Alright, hell yeah. So we have problems in general physics, and I'm kind of angry because I did problem 1.2, and we lost all of our footage. And you know how we roll? We do like 3-hour videos. So tomorrow I'm just going to do that one real fast. But I have to do this one, the start of this video, I just want to give you the answer, and then you can, walk through it. So I'm going to use that intensity to solve it. So anyway, it looks like this. We're going to accelerate. So this is a velocity graph. This is time. And we're going to accelerate for a short amount of time. We're going to go uniform and then come back down. What we do know is that the time over here for uniform is the same over here. And I'm sorry, the time for acceleration is the same as time for deceleration. I'm going to put a unit on this as time uniform, and this whole distance is time t. The main continuity that was just a son of a gun for me to realize is like, oh, the times for both these, I call them time for acceleration, TA. You can find both those times by saying the time for acceleration is just the time total, which we know is 25 seconds, minus that time uniform. We really want to know that. That's what we need an equation for. So that's going to give us the difference, and then divide by 2 will give you that. So basically you're taking this whole length, subtracting that. This remains, but divide that number by 2 and you get one of those. Okay, hell yeah. Because now we have to use kinematics to actually figure out what the hell this velocity is. The acceleration in this is they're not using a, they're using the w term, omega. And so cool. The velocity is just acceleration times time. Cool. So so the velocity max up here is going to be that acceleration times time. But what's time? Time is this TA term. So cool. So that's what that's going to be. This TA term. And then, but what we want to know is the distance that we're traveling. At the end of the, what the hell do we want to know at the end of the day? We want to find this time uniform, and they're giving us velocity average. And so this main equation is like, oh hell yeah, velocity average is distance total divided by time total. So cool, we know time total. I'm just gonna put a t on that, but time total is just t, and that's gonna be, or just t, 25 seconds. Okay, so now we're really using that. We're going to say velocity average is the distance, but what is the distance? Well, we got to get the average distance. That's going to be omega TA divided by 2. That's going to be the average velocity, and then but we have to we're going to take that average velocity, and then we're going to go, well, we got to multiply it by TA again. Cool. And then we're going to add, and then we can just see that we have 2 of those by symmetry. Cool. And then but then we have this component. What's the distance on the area under the curve? Is just, this v times tu, so that's going to be the velocity up there is just omega ta, and then times tu. Okay, but at this point we want to substitute this into ta, and we want to find tu. And so what we're going to do is this t is t total, this t is tu. I'm gonna turn this into a variable x. You know what I mean? And so we're gonna say ta is equal to t. This is the 25 seconds minus x divided by 2. And so then we can start doing that. Oh, and this was velocity average, so obviously you're going to divide by t total, which in this case we're just calling that t. So this right here is t total, and now we can do it. So I guess this 1/2 goes away, but we're still going to have that acceleration, and we're going to have this ta squared term. You know what I mean? So ta is this, so we're going to have t minus x. X is what we're going to find, and that's the time for this uniform divided by 2. And we're going to square that plus omega, and this is that term again, t minus x divided by 2, and guess what? Another x term. And this x is what we want to find, and that's the time uniform. Okay, and then we're going to just divide that by t. And again, t is a constant in here. X is what we want to find, that time uniform. Okay, so this term, we're going to say that's 1/2 t minus 1/2 x. And then we're going to square it. Cool. How I square is just, hey, let's just square this term. So it's going to be 1/4 t squared. Then square this term, plus, it's always plus, 1/4 x squared. And then find the garbage in the middle. You know what I mean? You have to, well, this times that, and there's a negative, so it's going to be negative, and it looks like it's going to be 1/4. But there's going to be two of those terms, you know what I mean, when we FOIL it. So it's going to be, it's not going to be 1/4, it's going to be 1/2, and then it's just going to be tx. Cool, so that's that term. And so we're going to throw that in right here. And then this term, you know, we can simplify it just by saying that's 1/2 t minus 1/2. We got to FOIL this through. My bad. So this is going to be 1/2 tx minus 1/2 x squared. Okay, now you can really see that a w is in both of them, and a t is downstairs. So we can really just factor that out. And now these terms you can just combine, you know what I mean, because this will all be in the parentheses, but we've already solved them. And so you can see that there's a negative 1/2 tx and a positive 1/2 tx. So those cancel. And I swear at this point, no. I've solved this twice, and it just comes out different each way, but it's the same answer. Okay, so now we have 1/4 x squared minus 1/2 x squared. This is the bigger one, so we're going to be ended up with negative 1/4 x squared. Cool. So in the parentheses, we have 1/4 t squared minus 1/4 x squared. All right, and that was all equal to the velocity average. And again, everything is a constant. They're giving you the velocity average, and I guess we can even solve that right now, velocity average. And I change everything to meters per second, just because that makes sense to me, because we want to find the time in seconds, not hours. So we say this is 72,000 meters. I think you can get there and divide by 3,600 seconds per hour. You know, that's 1 hour, and then hour pops up. What the hell am I even doing? No. This is 72,000 meters per hour. I guess I'll just write it one more time. So average velocity is 72 kilometers. 1 kilometer is 1,000 meters, and then 1 hour is 3,600 seconds. So anyway, all you have to do is go to 72,000 divided by 3,600. Obviously, not obviously, but I was just surprised. But yeah, 72 divided by 2 is 36. You know, and then so you get a factor of 2, but then there's an extra 0 up here. There's only 2 zeros there, so you get 20 meters per second. That's the average velocity. Cool. So that's known. The angular acceleration is 5 meters per second. So everything's in meters and seconds. So and then your time total is 25 seconds. And then so all we have to do is just solve for this x term, and that's actually pretty straightforward. So what we're going to do, I don't even know what we're going to do, but we're just going to go for it. So we're going to have this V average, T divided by omega, and that's going to have, now we're just left with this term. And it might as well just subtract this 1/4 T squared, and then equal to this 1/4 x squared. But we want to make this positive, and then so that's the easy way to do that. And then let's get this over here. So we're going to go 1/4 x squared is equal to V. I don't even know I'm doing all these steps twice. But now let's just multiply by 4. So we're going to have 4 here and 4 there. Cool. That cancels. And so now we're going to have x is equal to the square root of 4 velocity average. That's how they do that term. Times time. This time is that time total divided by omega, which is the acceleration for the problem, plus t squared. That t is that 25 seconds. And I already solved it in the problem. We know that this, and what the hell is this x? It's time for that time uniform. That's the variable we're solving for. And so if we do this, we get 4 times 20 meters per second times 25 seconds divided by 5 meters per second squared plus 25 seconds squared, and the square root of that. So we're going to have seconds squared, and the square root will become seconds. Here we meters cancel, seconds cancel, but this seconds is downstairs. It pops upstairs because it's downstairs, but it's under this meter, so it definitely pops upstairs. So cool. So then we have, hell yeah, we're almost under 10 minutes or whatever. 4 times 20 times 25 divided by 5 is 400 plus 25 squared is 1025, square root that. And no, we're getting the wrong answer. Well, what the hell am I doing wrong? 4 times 20 times 25 divided by 5 is 400. And this is 25 squared. So we're going to have... oh, damn. Why isn't this working? Because this should be 15, you know what I mean? So here's a way to check my number. If I have 15 squared there times 0.25, and then 0.25 times 25 squared minus that answer, and I get 100 divided by 25 times 5, and I get 20. So right here we're running into an error, so let's just do it one more time. We're going to have VT divided by omega. And then let's bring that stuff to the other side. So let's do 1/4 t squared minus vt omega, and that's going to equal this 1/4 x squared. And so now we got x squared, and then we can just bring up the 4 up here, so that cancels. Oh yeah, this is a negative. I don't know. Yeah, obviously that one of these should be a negative, because here was my equal sign, so I caught my error. Yeah, sure, this is positive over here, but we have to have this minus that, you know what I mean? So this is just negative. Yeah. So, but we can clean it up again. I'm glad I did that twice. So yeah, so we have just the square root of that is x. So we have x is equal to the square root of t squared minus 4vt divided by omega. Okay, hell yeah. So now if we do this, we got 25 squared minus 4 times 20 times 25 divided by 5, and the square root of 225 is 15. Cool, and 15 seconds was the answer. So there's your equation. There's your equation. So tu square root of t squared oh, I'm doing it wrong again. But yeah, the time uniform is tu square root of t squared minus 4vt divided by omega. Now, I think these problems have started to, I mean, they've sucked from the get-go. They are not easy, I swear. They feel not easy. But that's why we make 3-hour videos. But I didn't lose the footage for this one. I just lost the footage for this one. So we're going to do the same thing tomorrow. I'm just like, hell, let's just do the 5-minute solution. Because that's a bummer. Because I love to teach, you know what I mean? I mean, we just did pages on this to teach you how to do velocities and stuff. But anyway, I guess my 2 cents on this before we go is that, cool, this is an equation for this scenario where acceleration and deceleration are the same amount of times. And then you can change any of the parameters you want. You know, you can insert this total time. You can change the velocity average, which was that term, and they use that as the symbol for velocity average. And you can change the acceleration. You know what I mean? And so you do any of those terms, that's going to change this time for uniform. And the only thing that you can, the only thing that this problem does have limits, where if you don't allow enough time to accelerate, you know what I mean? And so like you go accelerate and then decelerate, and then just your time frames are too small. You just can't reach. There's going to be a peak where you just can't even reach this would be your max velocity, and then so your average would have to be right there. So in the case where you have no uniform time, where uniform time is 0, or obviously less than 0, because you can't reach it, that's the only stipulation on that. Anyway, thanks for joining me, and here's the rest of the video. Alright, hell yeah. So we have problems in general physics, and you know what I mean? All I had to do was just Google this name. It's Igor Irodov, you know what I mean? And that was the pronunciation on Google. I don't know if that's the actual pronunciation of the name, but at least I'm not butchering it. And so anyway, a viewer said, hey, can you do every problem in that book? And we're on problem number 3. And and then another viewer is like, hey, can you teach like 3 blue, 1 brown, if I get that right? You know what I mean? And sure, but no, I have no idea. You know what I mean? So I'm going to come from the perspective that I can be dumb as rocks and still figure out what's going on. When it comes to math and physics, it's all about juggling. You know what I mean? For the average person, you're going to be able to throw a ball up and then catch it. That's it. You know what I mean? The fact that you could have 2 hands and then throw 1 ball up, have that, and then switch it. Where the next moment you're going to throw that ball up and catch it. Even that might be too much for people. So that's why even if you, that's why I said in my engineering video that sometimes going from 2nd year to 3rd year, 3rd and 4th year in engineering at a college can be easier because your problems get so much specific. Your equations are just more specific, and when that happens, you're just like, whoa, you know what I mean? Hey, I'm just going to multiply those 2 numbers, and heck yeah, I get the answer, and we just go on with life. But then when you go back and solve some of these, trains moving with velocity problems, it'll just wreck you because you're just like, I can't do it because you have to juggle 3 different things. You know what I mean? Even just that, and then that's going to be too much for the average person. So what we do, this is why I love doing first chapter problems in physics books, is because they set the fundamentals up for every other problem that you're going to be doing going forward. And I really like Physics for Scientists and Engineers. We use that one. And even at the very beginning, they do tons of problems. It's like, can you just do a factor of 10? Like even this one. Like, hey, it says 72 kilometers per hour. Nah, just change that to 100 kilometers per hour. Cool. It says a time of 25 seconds. I don't know. That's probably pretty good. You could change it to 10 seconds. You know what I mean? And you're not going to be too far off. Obviously, yeah, you're not going to be too far off even with those. But anyway, so let's start in on this. I think I read it once last night. But we have a car moving rectilinearly first with an acceleration of 5 meters per second. And then so anytime you see the word acceleration, you know what I mean, definitely write the definition. And I first write it like this: acceleration is the change in velocity. And if you spell it out, divided by the change in time, you know what I mean? There you can say change in time in 1 second. You know what I mean? Because usually the units on acceleration, you can always do that, are meters second squared. And this is the units on acceleration. But I would write it like this: meters per second, and then divided by seconds. You know what I mean? I don't think I did a very good job of that, but now this is the same thing, because we're gonna, the definitionally, acceleration is a change in velocity every unit time, and we're working with seconds. So acceleration of gravity is going to be basically 10 meters per second per second. What this means is that if you jump off a cliff in 1 second, well, guess what? You're going to be going 10 meters per second times 2.25. That's going to be your speed in miles per hour. Kinda. It's like 2.235 or something. I don't know. It's pretty close. But I like to do times 2 plus 25% tip. It's a good way to remember that one. And so hell yeah. So we got an understanding of what acceleration is. And then you can write acceleration as change in velocity change in time that way, or you can just do dv dt. And if you ever get a number on this of 10 meters per second, write it like this, and you can even throw a number down here, 10 meters per second per 1 second. You know what I mean? So that's always a good, useful way to see the representation of acceleration. Because, yeah, this 5 meters per second squared means nothing to me. I live in America, and that's the tricky thing about being a physicist or an engineer when you're living in America. You have to deal with meters per seconds, and it's just, I don't... Well, but let's do that. Didn't we just say, so we have an acceleration of 5 meters per second squared. Didn't we just say that we can say this is 5 meters per second every 1 second? Sure. And didn't we say that if we multiply 5 by 2.25, we basically get the number in miles per hour? So 5 times 2 is 10. And then what's 20? See, I do the 25% tip because I don't know what 2.25 times 5 is in my head. But if my bill is $5 and I got to do a 10% tip like the old days, you know what I mean? I'm going to be given 50 cents. But now if I did a 20% tip, that's going to be $1. And then if I did, and then what's the 5%? You know, if I did a 10% tip, it's going to be 50 cents. But if I half that for a 5% tip, it's going to be 25 cents. So I'm going to have like, hey, 25 cents plus, 10% of 5 is $1. And then what the hell did I say? No, it's 50 cents. And then 20% is another 50 cents. So it's $1.25 would be my tip on this for if I was tipping 25%. 25% of this is 1.25. So I think we're all used to tipping 20 to 40% now. So now you can use that for your math game and be like, oh, hell yeah, I know what 2.25 is of that. Because I know what twice that is, it's 10. And then plus the 25% tip, $1.25. So this becomes 11.25. And check on reality, yeah, it's double plus a little bit extra. So we have 11.25 miles per hour. This is our acceleration every second. So now that's something. You know, I mean, we can now visualize that if I'm a car at a stop sign, I can probably do this. I can have my passenger have a stopwatch and be like, hey, let's see how fast we can accelerate. And when they say go and hit that stopwatch, I'm trucking it. And when they say 1 second, you know what I mean, I'm gonna read off the speedometer what my speed was, and maybe it's 10 miles per hour. Cool. Then we'll have that acceleration. And then at second 2, they're like second 2, and I say, hey, we're going 20 miles per hour. And hell yeah. And then let's do a check on reality, because you always want to make sure, what I want to make sure is that these problems are always consistent with what we find in nature, or just on an average, like, hey, we're having a car, and is this acceleration excessive? You know what I mean? So what we know is like, hey, we've always heard the term like 0 to 60 miles per hour in, you know what I mean, you guess, you know what I mean, what number would you put in right here? We've all heard that, 0 to 60 in, you know what I mean, if I said 10 seconds, would you be impressed? No. 0 to 60 in 10 seconds? That's a... So I think and I've already done a lot of research on this, not currently, but I just know that fast cars are about 0 to 60 in 4 seconds. You know what I mean? 3 seconds. I don't know if you can go 0 to 60 in 2 seconds. That might be a hella fast acceleration. You know what I mean? And so I would say that is too fast. So that's a check on reality on the low end. And then 4 seconds is your average fast cars. You know, even just, you know what I mean, your Italian cars that you can buy, you know what I mean, just for driving around will be like 4 to 4.5 seconds to go 60 miles per hour. So now what would that acceleration be? Because now you're changing your velocity. Definition of acceleration: change of velocity, change in time. Cool. So let's say we're going to change our velocity by 60 miles per hour in 4 seconds. And then let's get our calculator out. And we're going to have, and we could have done this one in our head, but we're going to have 15 miles per hour of a change in velocity every 1 second. Now it's okay This is where we get tripped up in America. Is like, well, you wouldn't write it like this. You could say, hey, 15 miles per hour every 1 second. Even the fact that acceleration of gravity in American units or English units is 32.2 feet per second per 1 second. This is gravity. So if you jump off a cliff in America, you're not going to be going 10 meters per second every second. Hell no. You're going to be going 32. All right, hell yeah. That was a pretty fun 10 minutes. So anyway, so in America, every second you're going to be going 32.2 feet per second. But this is the bummer in America. Nobody knows how fast 32 feet per second. And so then, I definitely love to do all the axioms. So, let's say this is, so 1 foot. 1 foot is like almost the length of your shoe. You know what I mean? So if you think about this, walking speed of 1 feet per second, a velocity of 1 foot per second, I think you should have this one in your head that this is slow. You know what I mean? Holy hell, this is slow. Now, if someone's walking 1 mile per hour, that's slow, but that's something. And so it's also slow, but which one's faster? That would be a good viral video of just like, hey, do you know which one's faster? Well, this is how I do it visually. Like, literally, your shoe size is almost a foot. So it would be like every second you take your other foot and then just like put it one after another, you know what I mean? And then, and this is how you'd walk. You'd put heel to toe, you know what I mean? And if you walk like that, just like 0, 1, 2, 3, 4. You're just going snail pace. Now, the average person can walk like 3 miles per hour, 3 to 4 miles per hour, but hey, walking 4 miles per hour, that's a brisk walk. And so walking 1 mile per hour, and maybe it's not. Maybe you don't know what's faster, 1 mile per hour, 1 foot per second. But just in general, like if I walk like this, I'd be like, whoa, this is hella slow. I don't want to walk like that. But if someone said, hey, can you walk 1 mile per hour? I think I would actually be walking probably like this. And so we're going to do a quick factor label method to just kind of prove that. What we want to figure out is feet per second, and we want to get miles per hour. And then, so that's all we have to do. So we're going to go 1 foot per 1 second. And now we need to change both of these. We need to change the distance, unit of length, and then we have a unit of time. No one does it like this. But anyway, we need to change our unit of length to feet to miles. So anyway, so we're going to use factor label method. We have to have feet down here. We got to cancel feet. So we're going to have 5,280 feet, and then that's going to be equivalent of 1 mile. So feet cancels, and now if we just did this, we would have miles per second. This is how many miles per second we're going to be walking. But a mile per second, like if you were walking 1 mile per second, well, you'd be going in that case, you'd be going 5,280 feet per second. But we're going 1 foot per second. We're going the actual inverse of this. Well, not necessarily the inverse of the units, just the inverse of that quantity. Okay, hell yeah, that was confusing. But anyway, so now we're going to convert miles. So we're going to say, hey, 1 mile. No, we already did that. We need to convert time. So now we got miles. We need to go miles per hour. So 2 ways you could do that. We'll do the slow way. We're going to say, hey, there's 60 seconds. We'll do it over here. 60 seconds in 1 minute. And then seconds cancel. Now you have miles per minute. You know what I mean? And this is a pretty decent one. If you're going 60 miles per hour, aren't you going 1 mile per 1 minute? You know what I mean? Aren't you going 1 mile per minute? You know what I mean? So let's do that factor, because yeah, like I do a lot of, and that's we'll finally get back to this problem, but we'll make it tolerable for us. You know what I mean? We're gonna say we're gonna use like 0 to 60 maybe. We're gonna use that part of the acceleration to figure out our average speeds, just because yeah, we know what 60 miles per hour in a car is, and then we know kind of our top speed. And so if we read the problem, basically we're accelerating. Then we're going to go uniform speed. And And then, so our velocity goes from 0, from a stop position. We're going to go up to a uniform speed, and then we're going to decelerate at the same rate. So there you go. And now, and what's the question? How long does the car move? So they just want the time frame on that. And we could find out both, because does it say, whoa. So, what does it, yeah, let's get the problem statement. So then uniformly and decelerate at the same rate. The total time of motion, okay, so the time from here to there is 25 seconds. The average velocity during that time, and they're just giving you the average. They're saying, hell yeah, that's going to be your V average. You do a little hat on top. It's not a vector sign. So sometimes you have this for your average, but I get it. In this book, they're saying this is the sign for average, because it looks like this for average is like a vector. That almost looks like a vector, but you've all seen, like, hey, find the mean. You know what I mean? This is what I'm typically used to. So probably for this problem, I'm going to do it like this. Hey, the average velocity, but it's not a vector. It's just the average velocity. So they're giving you the average velocity. And then how long does the car move? And then cool, so we know from our equation that if we have the average velocity, that's going to be, and what's the units on velocity? It's meters per second. And so over here we're going to have a distance, like, hey, it's going to be the total distance divided by the time total. And so what they want to know is... Yeah. And we already said the total time is going to be 25 seconds. You know what I mean? But they're asking, sometimes it's like, this is the hardest part of the problem. It's like, what the hell are they asking? They already said it's going to take 25 seconds for the entire motion. They want to know the time frame between the uniform. You know what I mean? Hey, how long does the car just move uniformly? And so we'll get to that, but let's go back to our factor label and then be kind of done with it. So we have 1 minute is equal to, sorry. We have 60 minutes is equal to 1 hour. We're trying to get to miles per hour. So minutes cancel, the seconds already canceled. And the other way to do this is just go 1 feet per 1 second, and we got 5,280 feet. That's going to be equivalent to 1 mile. The feets cancel. And then to get seconds to hours, we're going to go 3,600 seconds divided by 1 hour. This is one that you should always have in your pocketbook. You shouldn't be converting seconds to minutes and then minutes to hours. But you should. You know what I mean? Every once in a while you should do that. But then just immediately know that 60 times 60 is 3,600 seconds in 1 hour, and then the seconds will cancel, and then hell yeah, now we got miles per hour. So we got 3,600 divided by 5,280, and then we find that this is 0.68 miles per hour. Now it's not way different. We were saying that this looked hella slow, foot after foot. But, 1 mile per hour seemed a little bit faster. For me, I just have this in my pocketbook that, hell yeah, 1 mile per hour is faster than 1 foot per second. And if I wanted to multiply, if I said, hey, what do I, and the conversion factor here, like obviously 1 foot per second is 0.68 miles per hour, but if you invert that number, you get 1.46 repeating, and this is one. Alright, hell yeah. So I had to take a little break, but we're back, and we found that if we want to convert feet per second, if we want to convert miles per, so this conversion is if I have miles per hour and I want to go to feet per second, then I multiply by 1.46, and I'm never going to remember this one, 0.068. So if I want to go from feet per second to miles per hour, I'm just going to divide by 1.46, and I think this one's pretty simple to know because it's just very close to 1.5. So if I have 1.5 miles per hour, so that's the conversion. Hey, 1.5 miles per hour is the same thing as holy Toledo. 1.5 feet per second, a little bit faster, you know what I mean, than 1 foot per second, is going to be equal to 1 mile per hour. Okay, so that's the relationship. And yeah, it's just weird that you would spell it out like this, but if you had miles per hour, so if I had 1 mile per hour and I wanted to convert to feet per second, I got to multiply by that side, 1.5, and then I would get 1.5 feet per second. So there you go. But if I had feet per second, if I had 1 foot per second, I got to divide by 1.5. You know what I mean? So 1 divided by 1.5, or 1.5 inverse, is 0.66. You know what I mean? Kind of 0.6 repeating. And maybe I can remember that. There's no way I'm going to remember 0.68. But this 1.5, hell yeah. The way I remember it is just like, okay, it's like 1.5, but it's a little bit less. So maybe it's 1.4. But maybe it's halfway, 1.45. And that's going to be pretty damn close. But then I know it's like 1.4 and then something repeating, and it's close to, you know, it's not 1.43 repeating, but it's 1.46 repeating. And then, hell yeah, then I can actually, you know, kind of memorize that. And that's a total accurate number, because 5,280 feet exactly is a mile, and 3,600 seconds. So we go 3,600 by 5,280, invert that, and we get a perfect representation of feet per second to miles per hour. Alright, so holy hell. So now we got to get back to the problem. That whole thing was just showing you, yeah, no one knows the acceleration. No one knows a change in velocity. Because what were we saying here? In American units, we jump off a cliff. In 1 second, we're going to be going 32.2 feet per second. Now, if I didn't gain anything from that whole, you know, 5-minute tangent, 10-minute tangent, then it was useless. So, again, if I'm going 1 foot per second, that's hella slow. It's going to be less than, you know what I mean, 1 mile per hour. So, I know if I'm going 32.2 feet per second, my miles per hour is going to be less than that. You know what I mean? So now, you know, but that's as far as I got. You know, my intuition on this is just like, well, it's got to be less in miles per hour. And I'm just going to guess 20. I'm going to guess like 22 miles per hour. So every second, I'm going to go 22 miles per hour. But we can go 32.2 divided by 1.5, and we're going 22.46. We can go 32.2 divided by 1.4666, just repeating, and we get the actual answer. So, hell yeah. So just that, and I swear I did not, because it's just really good to get your guessing game, you know, on point or on target, and so we were very accurate, that 22 miles per hour. But now, there's more to this. I haven't done this one in about months, but I have done this, you know what I mean? I'd be like, well, I don't know what 32 feet per second is, but I wanted to know, hey, every second, how many miles per hour am I increasing in speed? Because now this number is very valuable. Because you should know that if you go cliff jumping and you hit the water like at 50 miles per hour, that's going to suck. You know what I mean? You want to be feet down, you know what I mean, and not belly flopping. Else you might go to the hospital or drown. And so you want to know, well, what's the time frame for your free fall? You know what I mean? How many seconds in the air could you be, which will determine the height of the cliff. So you can only be in the air for about 2 seconds, because you're going to go from 0 miles per hour to 22 miles per hour to 44 miles per hour. And that's kind of the top end. You know what I mean? So maybe you could, yeah, you could do a cliff that's just a little bit more than 2 seconds. But yeah, that puts you into the range of a cliff of like, you know, 40 feet to 60 feet, I think. Don't quote me on that. But we should be able to figure that out. In 2 seconds, you're going to be going 60. You're just going to be going double that. You know, so it's also really good to get, just kind of know. It's like, well, if that's my acceleration, after 2 seconds, what's my speed? 32.2 times 2. I'm going to be going 64.4 miles per hour. And this relates to our problem, because our initial velocity is 0 miles per hour. So if we do a little graph of 0 to 60, and we do this in the car, you know what I mean? So this is the one I bring up every time. Is like we have 0 miles per hour and 60 miles per hour. And guess what? We're going to be driving this for 1 hour. You know what I mean? So we're going to start our car and slowly increase our speed over the course of an hour to 60. No one's going to drive like that, but at least you can mentally visualize that. And that's the fundamentals of physics and math. Is just like, oh, I have a scenario that I can take. This is bizarre. This would be bizarre if anyone drove like this. The next town is gonna be, and in this case, hey, the next town is going to be 30 miles away, and you're just going to slowly increase your speed over the course of an hour perfectly. So, like, hey, by the time you reach the town, you're going to go 60 miles per hour. Like, no, that's such a bizarre scenario. No one's going to do that, but at least you can visualize that. You'd be like, oh, I could set up that scenario, and from this, we're going to find out that it's basically like we had an average velocity of 30 miles per hour over the course of that hour. So, hell yeah, we went 30 miles. And the distance is the area of this triangle. You know what I mean? So, anytime that you can represent something as an integral, or like, hey, the area under the curve is important, and represent something, it's just good to work on your basic integration skills. Because that's going to be the same thing for this. You know what I mean? In the course of 2 seconds, we're going to be going from 0 to 64.4 miles per hour. No, feet per second. We're working on feet per second. So here, same thing. We just have a very short time. We just have 2 seconds. But it's the same thing. What's our average velocity for that 2 seconds? Our average velocity is just half that. Well, duh, is 32.2 feet per second. And now we have an equation. What's the equation? The units are the equation. So if we have meters per second, we have meters, and then we have seconds. If we have these 3 parameters, how do we set these up in a relationship? Well, I like to do this one. So we do meters per second, and then we divide it by seconds. So there you go. No, is that what we do? No, hell no. We do meters divided by meters per second. Because if we did this one, this is nonsensical. This would just be meters divided by seconds squared. So that would maybe give us the acceleration, maybe. But anyway, so if we just have these 3 parameters, we divide distance by velocity, and then seconds pops to the top. So this gives us our time in seconds. So now this equation says distance divided by velocity is time. Kind of same thing here. And we have three different things. We can represent this in 3 different ways. So you could say distance divided by velocity is time. We could bring the velocity up here and say distance is velocity times time. What's the other one? So this has time, and then we could also say velocity is distance divided by time. So anytime, this is the cool thing about math and physics, or just equations in general, is like, hey, you have 3 things here. Like, this means that you can rearrange this equation in 3 different ways to get the parameter that you might be interested in. So what parameter are we interested in? Well, we were interested in the distance. So we know we have a time of 2 seconds. So that's going to give us this seconds, and we know we have a velocity. What we're interested in is distance. So you could say the units are the equation and do exactly what we just did. So if you do the units are the equation perspective on this, we have meters per second and we have time. What do we do to these 2 sets of units to get meters? So meters is already on top, time's on bottom in this one, and then time's on top in this one. So if we multiplied those 2 together, if we multiplied meters per second times seconds, hell yeah, we get meters. Now this might be like super trivial of like why are you even going over this? Is because there's so many times that you have a relationship between 3 items and you're just not visually understanding that you can represent this equation with 3 different terms in 3 different ways. You know what I mean? So like what I'm fascinated to do is use this same principle and do it with electricity. You know what I mean? That I don't even know is like you have resistance and you have current, and then you have what, voltage? Is that the, like, current is in amps, so you have amps, you have volts, and then you have resistance. I think that's the thing. But there's an equation that relates all 3 of those. And the same things, I would do the same exact thing. Oh, damn it, I don't even know what the equation is, but I would represent it in 3 different ways, and we'd be learning electrical engineering. Okay, but now we're just working about velocity. So cool. So what did I do? We were just going to multiply those two numbers together. So when we do that, 32. So now we can be just 100% confident that if we multiply 30, and you know, it looks like this: 32.2 feet per second times 2 seconds. Seconds cancel, and we get 32.2 times 2. So our total distance is 64.4 feet. All right, hell yeah. So there you go. So we found out that in 2 seconds, our cliff is 65 feet. And that's kind of the limit. You know, when I was in, you know, high school, we have cliffs out at our lake that are 65 feet, and they feel dangerous. It's too, you're in the air for 2 seconds, man. It's a lifetime. And you hit hard. You definitely want to wear shoes. I do. But yeah, that's my cliff jumping days are over. But there you go, 65 feet. So we put some numbers on it, and now we probably need to get back to the problem. Because, you know, or at least to the car problem. Okay, yeah. My bipolar is swinging around, and we're doing the Bill Clinton. Yeah, we can sweep up the, you know, we can talk about everything we were talking about, because the last thing we were talking about was the speed of the car being 4 seconds. I don't even know where the 4 seconds are. You know what I mean? It's just such a mess. Yeah, 4 seconds. So let's do that. New sheet of paper, and we know that the acceleration that's pretty fast for a car is 60 miles per hour in 4 seconds. And that's going to give us 60 divided by 4. That's going to be 15 miles per hour per 1 second. And now we wanted to figure out what this was in feet per second or meters per second. So let's at least do factor label method to get meters per second. So we got 15 miles, and this is going to be miles per 1 hour in 1 second. It's just an interesting way. You can represent acceleration like this. You can, acceleration where you're changing velocity. Your change in velocity can have different units than your unit time down here. You just have to be very careful using this in any sort of equation sense. Okay, so now we're going to use factor label, and we're going to get this in meters per second. You know what I mean? And you know, it's kind of confusing that we have seconds down here. You could also just say, hey, this is 15 miles per 1 hour, and I want to convert this to meters per second. If I did that, then I would have that number in meters per second, and then divided by seconds. And that's exactly what we want. So let's just keep it simple, and we're going to go 1 mile is 5,280 feet. Now, to convert miles, which is kind of a units of feet or American, I first go to feet, and then I go to inches, and then I go to how many millimeters are an inch. So I'm going to show you that whole process. So to get from miles per hour to meters per second, I first go miles to feet, and then I say that there's 12 feet in 1 inch. I'm basically trying to get to inches. So there you go. This is how many inches. And if you want to keep up, we do 15 times 5,280. So 15 miles, how many inches is that? Well, times 5,280, that's how many feet this is, divided by see, I already messed up, and I caught my error. So that's really cool that I caught my error, because if I did 15 miles times 5,280, that's 79,000. That's going to be a big number in feet. But if I want to know how many inches this is, I got to multiply by 12. So I did my factor label method wrong, and so down here I say 1 feet is 12 inches. You know what I mean? So that's what we also do with our videos. We really like to get errors, because from our errors we can we can see where we're making errors, and it's just fun to see if you can find your errors, and then see if you can just not make them or catch them quicker. That's my game. Is just like, you know what I mean. Do we already have a check on reality? And so let's do that. So our check on reality. of what 15 miles per hour is in meters per second. Well, didn't we say that if we have like meters per second, and this is where you might want to just come up with one. I know that like 55 meters per second is about terminal velocity, so it's pretty equivalent to 120 miles per hour. And why? Is because we take 55.5 times 2, you know what I mean, times 2.25, that 25% tip. And if we do that, 55 times 2.25, we get 123. So that's my check on reality. And so that would be like saying, well, if I knew how many meters per second, I would multiply that number by basically 2. So let's just divide this by 2, and then we get 7.5. So if that's what we're doing, if we got 7.5 meters per second, and then I multiply by 2, that's in general, I get miles per hour. Cool. So we know that our answer has to be pretty close to 7.5, and now we can do one better, and then we understand that we're dividing 15 by 2.25. We're dividing by that 2 plus 25% tip, and I can't do that in my head. If I'm just getting a general guess, you know what I mean? My general axiom would be like, hell yeah, miles per hour to meters per second. Well, and then I have to go like all the way around. I have to say, well, if I have meters per second, I multiply by at least 2. So if I have miles per hour, then, I guess I divide by 2. You know what I mean? And so that's my mental process. And talking my way through it, yeah, maybe I'm going to increase my ability to have that mental process go faster. But now I just really can't mess up. 15 divided by 2.25, we should be 6.6. So right now, had I done that error, we wouldn't have got 6.6. We would have got something way lower. And I would have recognized that right away. Okay, so we go from feet to inches. And now here is where I go 1 inch is 25.4 millimeters. Now this is an exact, America lost when it comes to engineering and the metric system. So our inch is precisely, the definition of our inch is precisely 5.4 millimeters. It's not 5.402, you know what I mean, repeating. No. It's just that, like, it's such a weird, you know what I mean, you can't state this enough that like America lost, you know what I mean. The meter has nothing to do with our foot. Our foot has everything, our feet and inches has everything to do with already the standard of a meter. I mean, it's just saying, hey, we want to say this is an inch, and then we're just being like, well, it actually is. And let's say this was our original inch, and it was 25.402 millimeters. Well, we just said, nah, we actually changed our inch to be 25.4 millimeters, and this is where you do the asterisk, because this is a precise exact number. And that's just cool to know, because there's not, some of these numbers aren't precise or accurate. And so that one is, though. So cool. So that's what I do. I go from miles to feet to inches, inches to millimeters, and now I go back from millimeter. I know that 1,000 millimeters is 1 meter. So this is the way I do factor label, and it's probably the most impressive part of this whole video, because you're just like, oh, no one explains this stuff. Anyway, so and then you do it in your calculator. You do 15 times 5,280, and then times 12. And then times 25.4, and then divide by 1,000. And we already right now we already got a wrong answer, and it's just like, well, no, duh, I didn't leave room to convert hours to you know, what this says. This is an accurate term, but this is saying meters per hour. You know what I mean? So this is how many meters per hour. So that's all I converted. Miles went to feet, went to inches, and then went to meters, but now I still have meters per hour. So when I type that in my calculator, it's not that I got the wrong answer, but I'm just glad. And I'm not setting this up on purpose. This is just how my brain works, and there's no way I'm gonna make every mistake in the book. And so that's why we have this check on reality, that our number should be, you know, in between, it should be close to 6 to 7. And we just got 24,000. And what gives? Well, we need to convert 1 hour into 3,600 seconds. And now we get meters per second. So divided by 3,600. And booyah, we get our answer, which is really cool, which is 6.7 0.056, you get warm fuzzies right now because you're just like, whoa, that's cool. Now I can have a strategy where it's just like in math and physics, there's no reason why I should ever make mistakes. You know what I mean? Because I've already used an educated guess. And you might make mistakes like on an order of 2 just because like the fundamentals, you're missing something. You know what I mean? It's like but you shouldn't have a magnitude of 10,000. You shouldn't be off by 10,000. You know what I mean? That is like, you can't be off by 10,000. All right, sweet. So now we are going to. So now we know that 60 miles per hour in 4 seconds is an acceleration of 6.7 meters per second per 1 second. You know what I mean? So that's what we did, and this problem says 5 meters per second. You know what I mean? So we have a check on reality, and now we can do the problem in reverse. We can be like, well, how many miles per hour is this? So let's do that. Let's go 5 meters per second squared, and now we can go a little faster. There's 1,000 meters in one. No. Holy Toledo. Yeah. 1 meter is 1,000 millimeters. So I always go to millimeters. I used to go to centimeters, but man, you're going to make an error there. But go from meters to millimeters, and then 25.4 millimeters to 1 inch. And then we're going to go inch. We know that 12 inches is 1 foot. And then we know that 5,280 feet is 1 mile. So right now, we know miles per second. Cool. But now we have to take this seconds, and this is where what we're trying to find is a bizarre one. We are trying to find miles per hour per 1 second. So like, because we don't want to find, what we don't want to find is miles per hour squared. That is not what we're interested in. We want to find miles per hour per second, and this is bizarre. Because if I did factor label method, if I have seconds down here, well, I gotta go 3,600 seconds are 1 hour, but I have seconds squareds here, so I would square this, and yes, this would give me miles per hour squared, but I don't want that. I want to leave one of these seconds down here. So I guess what I would do is I would say this is 5 meters per second times seconds. And I only want to convert one of these. So there's going to be 2 down here, 2 seconds of time, and I just want to convert one of them. So now one of the seconds cancels to hours. So now that this is going to give me miles per hour per second. Cool, let's do it. So we have 5 times 1,000 divided by 25.4 divided by 12 divided by 5,280 times 3,600. Now with the calculator, this is also just the cool thing to know about calculator, because I went through my entire college career of just like, oh hell no, I have to put these parentheses in. I have to say this is 1,000, and I'm going to multiply in my calculator 1 divided by 25.4 parentheses. Well, I just did 3 extra keystrokes to get there. So a calculator, the way it works is if I do 5 times 1,000, that's cool, divided by 25.4, and then if I divide by 12 again, that's not saying 5 times 1,000 and then divide by 25.4 I guess it's not saying this. It's not saying divide by 25.4, put that in parentheses, divide by 12, which would kick the 12 to the top. It's doing it this way in your calculator. When you go 5 times 1,000 divided by 25.4, and then do the divide again, then it puts it right here, and then divide again by 2,500, it puts it downstairs, and then the second you go times again, then it puts that term upstairs. You know what I mean? So then you can do this whole calculation without parentheses. So let's do it one more time. We got 5 times 1,000. Alright, got a new battery in. And so, heck yeah, we're just doing this in our calculator. 5 times 1,000 divided by 25.4 divided by 12 divided by 5,280 times 3,600. Now that's the one. For whatever reason, this always looked bizarre to me. Where you know, it's like, well, I don't know. Yeah, even dividing by and then dividing again, it just feels like you're gonna be like 1,000 divided by 25.4 parentheses divided by 12, but that's not what this does. It does exactly what, you know, I said it was gonna do. And cool. So now we have this is a change in velocity of 11.2 miles per hour every 1 second. And see how we don't need to double check. Even if you had a tiny error, it's just like, well, obviously our acceleration is going to be a little slower because we were saying that this was an acceleration of 6.7. Our problem says 5. And so every second we're going to be increasing our speed 11.2. And if we go back to even right at the beginning, we guesstimated that that was about 10 miles per hour. Cool. So now we're there. So yeah, so this is going to be our problem, and if we, because that's what I wanted to do. I wanted to get into miles per hour, because we, in general in America, we have a very good sense of like driving, even if it was like 25 miles per hour. And I said, hey, if I was driving 25 miles per hour for 15 minutes, I mean, just in general, you might not know specifically how to multiply that and get the answer, you know, do factor label, because you would have to convert units. But just in general, we kind of have an idea of like maybe that this is close to 30 miles per hour. And if I was going 30 miles per hour in 1 hour, I'd go 30 miles. But I'm only going for a quarter of an hour, you know what I mean? So maybe I'm just going a quarter of 30, you know what I mean? So 15 or 7, I don't know, you know, so... yeah, I don't know, but I just think intuitively we have a pretty good sense of that. So it looks like I went 7 miles, you know what I mean? And yeah, because like especially if you're on a dirt road and you're just like, man, I got a 7 mile, like I do it in reverse, it makes sense. I have 7 miles of dirt road, damn it, and I can only go about 30 miles per hour. It's going to take 14 minutes, you know what I mean? And if I can only go 25, well, you know what I mean, time's ticking, and it's maybe 18 minutes, you know what I mean, something like that. So that's using miles per hour is just, we're very good in America of knowing how fast we're going in miles per hour. So that's what I'm going to relate to in my videos because it's very helpful. I'm wondering if people from countries where you're going in kilometers per hour, if that makes sense to you, because even that's a bummer, because your physics books are going to be in meters per second, but your car in any foreign country, that's, well, I mean just anything that's not America, I guess, is going to be in kilometers per hour. But you still have to figure out kilometers per hour is not meters per second. You can't just take kilometers per hour and divide by 1,000. Now you just have meters per hour. Or I mean, if you take kilometers per hour and multiply by 1,000, you would get meters per hour. But that's not very helpful. And the fact that an hour is 3,600 seconds isn't a very intuitive number to divide by. To get meters per second, or multiply by, or however you do it. Okay, so let's start in on the problem. So we have a car starts moving, and then rectilinearly. I think it just means linearly. I'll have to look that up. I mean, yeah, that's fascinating. You know, some of these terms I'll look up later. It's like I have, you know, it sounds like you're just moving in a straight line, but it's just a fancy way to say that. I don't know what this part of that word means. Anyway, so we initial velocity is 0. And yeah, so cool. So and then we're gonna say this is just 10 miles per hour every 1 second. So let's just do a very loose guess. I mean, if this is a normal problem, like how fast are we going to be? Oh, and it says our average speed is 72 kilometers per hour. So we need to figure out what this is in miles per hour, especially if we're going to do the whole problem in miles per hour. So let's do that. So we have factor label method, 72 kilometers per 1 hour. And now we're going to go, hey, 1 hour. We'll do the time first, is 3,600 seconds. So now we have kilometers per second. And now we're going to say 1 kilometer is 1,000 meters. And then so we have meters per second. And then we're going to say 1 meter is 1,000 millimeters. Cool. And now we have millimeters per second. Why I went to millimeters is because this is the only way to go. For me, I like to go from millimeters to... and if you didn't, the other one to know is that, well... is that if you're just trying to find if you got meters and you're trying to find miles, then 1609 meters is equivalent to 1 mile. You know what I mean? So 609 meters is approximately 1 mile. It's not exact, and there is a decimal place here, but I don't think the decimal place is of any significance. I think it's almost like 1609.04, or maybe it is 16.94. I forget. Maybe it is like halfway. You know what I mean? And it's pretty darn significant. But 1609, just at the end of the day, that gets you there. So even right now, we could be like, okay, 72 times 1,000, we have this many meters, and divided by 1609. So now we just know from this we're going 44.7 miles per hour. So that's the check on reality once we do factor label method. So I have we converted to millimeters, and I got 25.4 millimeters to 1 inch, and then 12 inches in 1 foot, and then 5,280 feet. Feet cancel in 1 mile. All right, hell yeah. So that's now miles. Oh, and my bad. We wanted miles per hour, so this was the first thing I did was just dumb. You know, so we don't need that. So now I have so I want to keep hours down below, and now we have miles per hour. We're going to do this in our calculator using that strategy of just 72 times 1,000 times 1,000 divided by 25.4 divided by 12. Now, this is the most important thing about doing physics and math is like, you know what I mean? You're going, see, look, I just typed in an extra 0. You got to catch those errors along the way. And there you go. So now we have a speed of 44.7 miles per hour. And the reason why I'm spending so much time on these first chapter problems is because you want to develop your skills. The whole... Like, I swear, the first chapter, you should spend a whole month on first chapter problems in engineering that you already could get the answer very easily, but what you're going to do is figure them out like 100 different ways. Like, guess them, you know what I mean? So it's a combination of using guessing techniques. In that first chapter of physics books, like we said, it's a combination of turning things into like, hey, like we just did, 10 miles per hour. Cool. And now we're going to go, you know, and maybe for our problem, you know, we're going to go 1 hour or something. Okay, so that's why we don't make mistakes. We already did this, and then we have a check on reality. All right, so now we know that this is our average speed, and even right now we have an intuitive sense. So the total time of motion is only 25 seconds. Now that's pretty wild. If the total time for motion, you know what I mean, let's say it was a normal road trip, and our total time for motion was 1 hour, and then we started at a stop sign, we were going 0 miles per hour, and then we ended at a stop sign in our town going 0 miles per hour. That's this problem. Hey, we start at 0, we get up to some velocity, go for that velocity, and then decelerate and hit that stop sign. Now, if this was the case, and our average velocity, and they still said our average velocity was 44.7 miles per hour, from this scenario, you know that, well, maybe you don't. I mean, at the end of the day, you can just say, hey, this was, just pretend that you were going that distance for the entire time. And then, so how, so then the question is like, well, you know, they said you're going to, oh, there's two different things here. Cool. So we're gonna lay this out like they have it. They're gonna say, hey, they're gonna give us this total time. So we're gonna say, hey, we drove for 1 hour, and we had they're gonna say the average velocity was 44.7 miles per hour. You know what I mean? So from there we know our distance, because we know that the velocity, and then that's going to be in meters per second, and if that's going to be equal to, well, it looks like we have distance and time, so it's going to be dt, and our distance is 44.7 miles per 1 hour. Oh, what the hell am I getting at? No. This is the average velocity, and then we have an equation, and this is the time. So if we wanted to find the distance we were going, well, 44.7 miles per hour in 1 hour. That's why we're using miles per hour, because you can just, it's the whole juggling thing. You know what I mean? We go back to this. Sometimes you can only juggle one thing in your hand at a time for the entire problem. You know what I mean? And that's kind of... At the end of the day, I like that strategy. I would rather spend 5 hours, juggling the same thing in my head, and getting the right answer at the end. There's something super satisfying. I consider this the magic trick. You know what I mean? There's times if you got a gun to your head and someone's like, hey, test time. Can you solve that problem in 4 minutes? Well, that's a different strategy. You know what I mean? You're just like, you know what I mean? And it's risky, too, because you might get the answer right, or you might get the answer wrong, and then you just move on. But your probability of getting the answer right and wrong might be 50-50, you know what I mean? Because there's so many chances for errors. All right, and what we're trying to do is see if see if we can. So we got 44. Yeah, and holy hell, well, we have to change this to 45 miles per hour. You know what I mean? Because even right there, why the hell say 44.7 the entire video? So our average speed is 45 miles per hour. So even just right there, that's amazing. It's just so refreshing, because right now I'm just like, oh yeah, if I drove 45 miles per hour for an hour, I went 45 miles. I don't even know if I said that right. 45 miles per hour. Cool. But we know, and that this is the actual distance that we went, because it says, hey, it says this is our average velocity. And but what I'm proposing is like, well, does that mean that we drove 45 miles per hour? Does that mean that we started at the stop sign going 0, got up to speed, and then drove 45 miles an hour? And the answer is no. You had to drive slightly faster, because you were going pretty slow here. But in our acceleration zone, going back to what the average velocity was, well, our average velocity for that little short time period was only half of 45. Let's just say about 20. 20 miles per hour was our average velocity in there. And then our average velocity decelerating for the stop sign was also 20 miles per hour. So those are two slower regions that occupy up some of that hour. And so you have to be slightly. But I did this drawing because it's basically who cares. You know what I mean? This basically says that for this scenario, the time that we're driving at this constant speed is going to be 1 hour. You know what I mean? The time to get up to speed is so negligible. Because if we're saying that we can go from 0, for our problem, every second we can go 10 miles per hour more. So you're going to have 4.5 seconds to get up to speed, and then 4.5 seconds to brake at the end. Because that's the other thing. They said the acceleration is the same upon braking. All right, I'm going to take a little break. All right, hell yeah. So we're back, and I thought of something pretty cool, because there's a chance that, you know what I mean, the part where we actually go a uniform speed, that they want to know how long that time frame is, that might be 0, you know what I mean? And it was kind of cool because it sets up a check on reality, that if the part that you go is 0, well, it has to be a perfect, you know what I mean, where it has to be perfect, where if that you still go an average speed of 72 miles per hour, because if that's less, if your acceleration, I mean, there's a chance that if you can only accelerate like this, but you know this time frame is only 10 seconds. Let's talk about that, because we know that our acceleration is 10 meters per second. We know that we have to increase our speed and decrease our speed. We got to go from velocity 0 to velocity 0. And so if we only have 10 seconds to deal with, now we have 5 seconds to increase our speed. So we're going to go from 0 to 10 to 20, 1, 2, 0, 1, 2, 3, 4, 5. And so we're going to go 0, 10, 20, 30, 40, 50. We're going to hit 50 miles per hour, but then we're instantly going to go down. So at second 6, 7, 8, 9, 10, we're going to go 40, 30, 20, 10, and 0. And in this case, if we did that, and we only hit a 50 miles per hour because we only had a 10-second window here. What is our average velocity here? Now this one you got to be careful, because we have two different triangles. But if we're dealing with triangles, isn't it still just halfway? You know what I mean? So sometimes I get messed up where I definitely have to convert this into one triangle of 50 and then the time frame of 5, and then that's like going 25 miles per hour for 5 seconds. Cool. And if that was the case, then that's the average speed there. But then on this side, it's like, well, it's the same. Then I'm going an average speed of 25 miles per hour for 5 seconds. Cool. And so it is the same. It's the same thing as saying, hey, but yeah, for whatever reason, it doesn't. When the triangle is like this, it messes with me. Where it's just like, wait a minute. If I'm going 0 there and 0 there, it seems like it would be like 50 divided by 4. You know what I mean? And then per 10 seconds. But that's not the case, right? Because your average speed from 0 to 50. Your average speed for half this is 25 miles per hour for 5 seconds. So I mean, your average speed is 25 miles per hour. That's just your average speed. Doesn't matter what the time frame is. If you start at 0 and go to 50, and you do that linearly, your average speed for whatever time period that was 25 seconds. You do the same here. The average speed for this time frame, if you're slowing down linear, as long as this is linear and not like this or like that, then your average speed is going to be 25 miles per hour for that time frame. And just in general, you could say, hey, your average speed is 25 miles for this entire time frame. But I swear, every time I have a triangle that looks like this, is like I second guess myself that you can just draw a line right in the middle. That will be your average speed. So cool. So we're going to have an average speed of 25 miles per hour for 10 seconds. And then what's that in? So yeah, let's grab a new sheet of paper. And for that scenario, where your time frame is just 10 seconds, you're going to have a velocity average of only 25 miles per hour. And now we want to do factor label and just see how far off that is. Like what we did right there is just we totally undershot it. Like this problem is just like, hell yeah, we're just going to pretend like two towns are really far apart, and then yeah, our average, this flat section is the total hour. So if we had that, if we were able to accelerate very, very fast, you know, from that stop sign, get up to that average speed, and then come down, then the time, how long does the car move uniformly for that chunk would just be about 25 seconds. So we would just say about 25 seconds. But because we're getting up to speed and then instantly slowing down, well, no, this uniform time period might be 0, time 0 right there. And so that's what we're doing, and we're showing right now. I'm showing you where it's just like, yeah, if we really reduce this to 10 seconds, we're probably not getting an average speed of 72 kilometers per hour. So this is 25 miles. per 1 hour, and now we got to convert to kilometers. So let's just do that the fast way. I'm going to say that 1 mile is 1,609 meters, and then 1,000 meters is 1 kilometer. So there you go. And now I just converted kilometers per hour. So I'm going to do 25 times 1609. See how knowing just that one aspect, that and how do you know that 1,609 meters is 1 mile? I went through at least my first year of college not making the like I ran the mile in high school, and around the track you got to go 4 times around a 400-meter track. So you run a 1,600, and they call it the 1,600, but they also just call it the 1 mile. You know what I mean? And if you wanted to run a mile, well, you'd have to run 9 meters more, and that's 9 extra steps, 9 extra long, striding steps or whatever, and that's going to take you definitely almost a second per step sometimes. You know what I mean? So your mile time is going to increase by at least 5 seconds. If you run the actual mile, you know what I mean, and you're trying to break 4 minutes, yeah, and you ran the 1,600 and had a really good time. I'm going to brag right now because I was able to run the mile. I just think it's weird because my body's falling apart right now, and I'm 41. But I ran the mile in 4 minutes and 26 seconds. And that was cool. I only ran that once at state, but yeah, I just put in a lot of effort that you're cycling and doing like 10-mile runs in the evening, and then waking up doing runs in the morning, and doing 2-hour cycling. But anyway, it was just, and that didn't come. Like, I went from like a low 30s, like 435 to 434, and then at state just really pumped out the extra juice to get it down there. That was fascinating, but that was senior year, so it didn't chisel away at that anymore. But yeah, it's just fascinating that 1,600 meters is a mile. So you just say that. You can just be like, hey, 1,600 meters divided by 1 mile. You're going to get the same answer. So let's do that. Let's go 25 times 1,600 instead of this, and divided by 1,000. And that's going to be 40 kilometers per hour. So we need more time. So now it's kind of cool. Well, let's just slowly increase our time. Let's go to time as 20 seconds. So now if we do that, we're going to go 0 to 10 miles per hour, and we're going to go 100 miles per hour in 10 seconds, and then we're going to go back down to 0 miles per hour. So hell yeah. So our average speed here is going to be 50 miles per hour. We just doubled our average speed if we did that, and we would have 80 kilometers per hour. So in that case, we would have a higher average velocity. So even at 20 seconds, which isn't even the problem, if we increased and then spent no time going uniformly and then decreased, so we went 10 seconds accelerating, 10 seconds decelerating, got up to 100 miles per hour, we would have an average velocity of 80 kilometers per hour. It's close, but we only went for 20 seconds. So now you can totally see that if we actually go for 25 seconds, we are going to increase, and then we are going to have a flat zone. So even just right there, I can almost 100% positively say that we will have some sort of time where we go uniformly. And now I think it's very useful to guess. I'm going to say, hey, let's go 5 seconds uniformly. And then we're going to go 10 seconds increase. No, because we already did that. Increasing by 10 seconds got up to us 100 miles per hour. Like if we took that thing and did this with it, well now... Alright, so let's see what that would do to our average speed. You know what I mean? Because... again, this more looks like the one we did in the beginning. Just, hey, it looks like we're just, whatever this uniform speed up here is probably kind of our average speed. So if that was the case, if this thing is more, and we're just saying it's the entire thing, 100 miles per hour, If that was our average speed, whoa, we would have 160 kilometers per hour. So see how useful it was just to take one of these and convert it from 25 miles an hour to 40 kilometers per hour? Because now I can say, hey, 50 miles per hour is 80 kilometers per hour. And then 100 kilometers per hour, 100 miles per hour is 160 kilometers per hour. And even, this is where America, it sucks, because even on our cars we have the kilometer per hour gauges, but no one looks at them. And so, even like 100 kilometers per hour is about, what is it? Is that 60 miles per hour? Just a little bit less? Maybe you have these relationships. 40 kilometers per hour is 25. Oh, so if that's the case, then 100 miles per hour is going to be, never mind. But yeah, if you doubled this, yeah, that's what we're doing. But anyway, yeah, so just to have a check on reality of like, is there any association between kilometers per hour and miles per hour that I recognize? And it was a skateboard video of someone going 100 kilometers per hour on a skateboard, and that was very close to like 55 to 58 miles per hour. I don't even know, and I don't want to do the factor label method to know that exactly. But can we figure that out? If we have 100 kilometers per hour, that's going to be 100,000 meters, and then we're going to divide by 1609 to get mile, right? So just do that, divided by 1609, and that's going to be 62 miles per hour. Okay, does that confirm it? Is 100 kilometers per hour just over 60 miles per hour? Yeah, because I think the skateboard video that I was watching said maybe they were going like 95 kilometers per hour. I think they prefaced it like that, 90, something like that. But yeah, 90 times 1,000 divided by 1,600, yeah, 55. So 90 kilometers per hour is pretty close to 55 miles per hour. Hell yeah. And that's essential. Even what I'm doing right now is really locking in the relationships between miles per hour and kilometers per hour. The stuff that we've done from feet to seconds to meters per second is just very useful. Okay, so let's understand that now that this, if we did this, because we were just saying, we're going to go for 25 seconds. Let's just do this for 5 seconds. No, we can't do that to get the actual answer. What we have to do is decrease these two sides. So we're going to say, and then definitely increase this. So let's say this is going to be, I don't know, let's just say 12 seconds. You know what I mean? So we have 25, or I don't know, let's say it's 13 seconds. 25 minus 13. And then you have 6 seconds on both sides. So we're going to make this 13 seconds, 6 seconds there, 6 seconds there. So now our problem says we're going to go in 6 seconds, we're going to go 0, 10, 20, 30, 40, 50, 60. So you're going to get up to 60 miles per hour, and then you're going to go 60 miles per hour, and then you're going to drop. So we're going to have an average speed here of 30 miles per hour, an average speed here of 30 miles per hour, and then an average speed here through that section, well, we're going to go 60 miles per hour. Okay, so now we need an equation because we're going 6 seconds, and 13 seconds. Now we need an equation that helps us figure out the average velocity. What is the definition of average velocity? Well, average velocity is the total distance divided by the total time. And so right here, the total time is going to be 25 seconds. So we know that, 25 seconds. Now the total distance is going to be, well, we're going 30 miles per hour for 6 seconds. That's the bummer here, is because you would need to kind of convert this stuff. Like how many, do we convert to meters? Yeah. So let's go back and find, like, obviously right now having this in miles per hour isn't useful, but maybe let's do it. Let's still stay on miles per hour. So we're gonna go miles per 1 hour, and now we're going to we have velocity. So if we have like meters per second and we want to get distance, well, we're going to multiply by time. So this time value, and these aren't divided. I'm just saying that that's the time value for that section. Okay, so we're going to multiply by 6 seconds. Well, we got to use factor label. So we need to convert this into seconds. So we're going to go 1 hour is 3,600 seconds. That wasn't too bad. And now we need to yeah, this is brutal doing it this way. And I actually want to just get to a quick relationship where I don't have to convert these. And we probably don't need to, because we could come up with just a bizarre, we could do 30 miles per 1 hour times 6 seconds. Well, this does give us something. It gives us, so we have 30 times 6. This gives us 180 miles per hour times seconds. You know what I mean? Is that something you can actually do, or can you not separate those things? I don't think you can. I don't think you can do that, because it'll all be lost in the wash. But yeah, I'm gonna spend about 2 minutes trying to do a different method. So we have 30 miles in 1 hour times 6 seconds, and then this is gonna that's distance plus, and then we have 60 miles per hour times 13. Yeah, miles per 1 hour times 13 seconds. And now this one is just times 2. We just have 2 of those. Yeah, we could do this. So this is fascinating to me. Let's clean this up just a little bit. But what we're going to have is 2 times 30 miles per hour times 6 seconds plus 60 miles per hour times 13 seconds. It is just fascinating that you can do things different ways, and the crux of understanding these problems, or not the crux, but just the difficulty in understanding these, is like, hey, you might only know speed in miles per hour. You know what I mean? So if someone says, hey, miles per hour, and I'm going to go for 1 hour, that's easy to make an association. But if someone says, hey, I'm going 60 miles per hour for 6 seconds, how far did I go? You know, like, no idea. You know what I mean? Maybe you could guess, you know, and be like, okay, a car is here, it's going 60 by me, and in 6 seconds later, yeah, it's hella down there. Maybe a football field down there. Yeah, that's a pretty damn good guess. And that's what we're doing with first chapter physics stuff. Like, even just that's a gold guess. Be like, oh, okay, I have this understanding of cars going 60, and if a car goes by me at 60 miles per hour, and I go 0, 1, 2, 3, 4, 5, 6. Oh, hell yeah, I'm going to change my guess. I would say on the high end, it'd be 4 football fields away. You know what I mean? And that might not even, like, if I was going to say 2 football fields, but maybe 3, and I don't even know. That guess could be way low, but at least that would be a target guess of, and now, from that perspective, we're going to do the factor label on that one, because that's fascinating, but we can show that, heck yeah, so we do have this relationship where we can now add, can we add these things up? Or can we not? You know what I mean? I don't know if we could. Yeah, that's the bummer. I don't know enough. But if this says 2 times 30 miles per hour, nah, I just can't. I can't do that. So we're going to take a pause on that. Alright, hell yeah. So took a little break, but man, this is such a cool representation of math and physics. Is you might want to explain something using concepts of numbers, but then you might just get frustrated. You know what I mean? You're just like, oh, I'm trying to do something here and it's not working. But all we have to do is change seconds into hours. You know what I mean? So we could just, if we have 6 seconds, we go 3,600 seconds divided by, so we just got to divide that by 3,600. And so, but that's going to be the main frustration in doing problems, is just like where you're trying to tackle something and you get exhausted from the process, and you're just like, I don't want to do it that way, or I don't even want to go through the simple steps. I might make errors, and then I have to account for those. And so we're gonna draw that scenario again. We're gonna have 6 seconds there, 13 seconds there, and then 6 seconds. So that's kind of almost visually representative. So we have 6 seconds, and 13 seconds. I just need to check on reality that 12 plus 13 is 25. That's going to be the total time. And we know that just in general, our problem says we have an acceleration of about 10 miles per hour per 1 second. So every second we're going to increase our speed by 10 miles per hour. But if we brake, we're going to decrease our speed by 10 miles per hour every second. And, you know, from our problem, we saw that was like 11. You know, it was actually like 11.2. But we're going to be satisfied with just getting we're still in the motions of just trying to get an accurate guess of this time uniformly. And then once we do, then we can hey, have that check on reality. Then we can actually get the answer. You know, that might be the next thing. But then the third thing is we'd be like, well, how did we do that? What things did we multiply? And then we can get an equation with just letters. You know what I mean? So that's kind of cool there. Okay, so here we're going to be going 60 miles per hour. We're going to start at 0. And then we're going to go 60 miles per hour for a certain amount of time. And then we're going to go to 0. And I guess I want to go back to this because what did we say 72 kilometers per hour is? Oh, well, I already got that. It's 72 times 1,000. This is 72,000 meters per hour divided by 1609. So we already know that, hey, this is the same average velocity of about 45 miles per hour. So even right here, does it look like our average velocity was 45? I mean, just even showing this visual representation, hey, these look about the same. And I could say, well, your average velocity is 30, but you looks like you went 60 for quite a ways. Now, are these is this going to be 45? You know what I mean? And how many different graphs could we get to get 45? Let's say this is just our full time, you know, and maybe this is half and this is a quarter. If I just went 60 miles per hour for 3/4 and then went 0 for this entire time, well, would that be 45? Would this say that I went 60 miles per hour well, I went 60 miles per hour for 3/4 of the time, and then went no miles per hour. So even visually, that one's hard for me to represent. But if I did this, if I went equal amounts of time, well, hell yeah, it looks like I just went 30 miles per hour. So in that case, this is 30. And in this case, well, this came up on the first problem. Well, it seems like if these two are equal, I can easily use that equation that says whatever this velocity was 60, whatever this velocity was 0, you know, this representation is the same as just decreasing from 0 to 60. So then I can break this up in two little chunks. I can say, hey, this is 60 miles per hour. And yeah, the average velocity through here is 30. Cool. So then I can take that and then go halfway. And so this is the same thing as going 60 and then 30. Well, now this is really at the two equal time frames, and this would be like the same thing as going 45. And the equation for this is 60 plus 30 divided by 2. That's going to be the average velocity for that, you know, time frame. And it comes from, and let's go back to this one where you're just going 60 and 0. This is the same thing as going 60 and then down to 0. The average velocity, the area of that is equal to the area. I don't even like to think of it as the areas yet, you know, because you just want to get kind of just a general. When you drive in your car, you're not thinking about areas under the curve. You're just be like, hey, this is my speed and this is my time, and I kind of know maybe like how far I went. Or I kind of know, and if I know, you know, you can easily figure out your average speed. Okay, so that was a cool representation, and And but this wasn't what we had. Over here, so we can do that visual representation. It looks like this is about half. So we're going to be, here we're going to be spending half our time going 30, and then the other half our time going 60. Oh, cool. So isn't that, I mean, this is what this is. This is about 12 seconds. Well, we're just going to say this is approximately 12.5, and this is approximately 12.5, and then we have an average speed of 45. Oh, hell yeah. That totally is our problem. So that's how I like to do things, is just like, hey, do you have enough intuition to just kind of guess the right answer or get close or you know, improve upon your guessing skills? So now, I'm even just visually, I'm pretty satisfied that the time for that uniform part is about 13 seconds. Because I know if the time for the uniform part is half, or 12.5, which might actually just be the answer, I'm not going to go there. I'm not going to say, hey, this is like a multiple choice A, B, C, D, and then be like, well, it must be half, because why would they choose anything different than that? But that's pretty darn good, because if we're... But not really, because if we're increasing our speed... you know, if we go back to the actual problem, our acceleration is actually 11.2 miles per hour, and if we're going for that little extra 6.25 seconds, well, we'd be going 6.25 times 11.2, and we would actually be going 70 miles per hour. So even if we did the problem like this, where we said we had 6.5 seconds, 6.5 seconds, and 12.5 seconds, well, we'd be going 70 miles per hour right there, 70 miles per hour right there, and our average speed would be 35 miles per hour for half the time, and 70 miles per hour for the full time. So our average speed for the whole thing would be 70 plus 35 divided by 2. And so our average speed would be 52.5 miles per hour, which we know and how do you get meters per second? You'd take miles and then multiply by 1609. This is how many meters, and then divide by 1,000. So our average speed in this case would be 84 kilometers per hour. So we know from our actual problem that this time frame is not more. You know what I mean? It's actually excuse me. This time frame is actually larger. Because the time increasing our speed is going to be less, so our velocity uniformly is less, making our average velocity come down. So I'm just going to say, hey, maybe these two are 5 seconds each, and then the actual time in between is 15 seconds. And so now we kind of have a check on reality. We don't even need to... we basically did what we figured out the average velocity of this. You know what I mean? From that standpoint. But no, we wanted to figure out the average velocity from this equation. So let's do that. So we have average velocity as distance total times times total. Our times total is 25 seconds, and then we're going to have our distance, and we need to figure out our distance in miles per second. So in this scenario, we're going to be going 60 miles per 1 hour. And now we have to, and then we're going to be going for 6 seconds divided by 3,600 seconds per hour. So 6 divided by 3,600 is how many hours we're going. And then we're going to add that to the middle section, which is 60 miles per 1 hour times 13 divided by 3,600, sorry. And this is how many hours. Hours cancel, so this is how many miles we're going. And then we're going to do that one again on the way down. Oh wow, it's so fascinating how many places I can make errors. So the average velocity on the way up is just 30. And so I'm sorry I called that 60. So we have 30 miles per hour times 6 divided by 3,600. Now the uniform part, we're going to have 60 miles per hour for 13 seconds. And how many hours is 13 seconds? Well, it's 13 divided by 3,600. And then obviously over here we're going to have an average speed of 30 miles per 1 hour, and then another 6. We're doing this one. We're doing that one. And then 6 seconds divided by 3,600. Cool. And then so, I mean, what we're doing here is just nonsense, you know, stuff where it's just like, hey, can I just keep the ball going? Can I do just a bunch of arithmetic where I'm going to catch errors like that and come to concise answers that are going to make sense? But this is cool because now what I'll get is I'll get a and you know, if we want, I'm going to get miles. I'm going to get miles, but I'm going to get miles per second. And so we want to convert that to miles per hour. So this seconds, I'm going to divide 1 hour divided by 3,600 seconds. And I'm going to multiply 25 seconds. Seconds cancel, so we'll do that too. So that's all I had to do, is not run into a block, but convert my times in seconds to hours. That was it. So we're going to do 30 times 6 divided by 3,600. And I don't even need to use parentheses for this, you know what I mean? Because now I can just add it to 60 times 13 divided by 3,600. Now I can add it to 30 times 6 divided by 3,600. Now right now I got to throw a parentheses or just enter, maybe store that as x, and then come down to here, 25 divided by 3,600, and now I'm going to go x divided by that. And so this gives us my velocity of 45.6 miles per hour. And isn't that what we were expecting? You know what I mean? Yeah, that's 100% what we were expecting. These distances were about the same, and then we did that, and now we have a check on reality. But that was just fascinating to do it from the arithmetic approach and not get too overwhelmed. Okay. But we know that this isn't the case because we're actually going to increase our speed 11.2 meters per second every second. And so even if we did that, 11.2 times 6, we'd already be going 67.2. So we would already be increasing our speed. So we know that this time frame is about 5 seconds, this one's about 5 seconds, and that means this one's about 15 seconds. Okay, hell yeah. So now I guess, I mean, what do you want to do? Do you want to try to guess the right answer? Well, let's do that. It's kind of fascinating and fun because I think the hardest part about math and physics is doing the arithmetic. So we're gonna, you know, and just, you know, keep doing it. You know what I mean? So if I'm gonna say this is 5 seconds, this is 15 seconds, and this is 5 seconds again. I know my acceleration is so now what we should do to get the actual answer, if we think these are the time frames, we should convert everything to meters per second. So we're going to convert this velocity of 72, and I can even just do it right now, 72,000 meters per hour, and I need to convert that to seconds. So I'm going to say 1 hour is 3,600 seconds, and I got 72,000 divided by 3,600. Oh, that's really easy. This is just 20 meters per second. So yeah, they used 72 divided by 36 by 2. You know what I mean? And so that's something where I could not see that. You know what I mean? If I was in Europe and this is constantly what I would be doing with meters per second and kilometers, I would see that relationship right away. But now our average velocity for this whole thing is 20 meters per second. We're going to increase by 5 meters per second. So I'm glad we used miles per hour because we understand what that is. Like, it's a lot nicer in meters per second because I can be like, oh, okay, I'm going to every second I'm going to increase by 5. So we got 1, 2, 3, 4, 5, and I'm going to go 5, 10, 15, 20, 25. So I'm going to be 25 meters per second up here. You know what I mean? And again, go back to the definition of acceleration. It's change in velocity, change in time. And we know that our acceleration is going to be constant, and it's 5 meters per second squared. So right here we have an equation, kind of an equation of 3 different things, and we know one of them. And we just said that we picked the other one for time. So if we have this equation for acceleration, let's write it in all three ways. Change in velocity, change in time, that's one of them. Let's do change in time is equal to change in velocity acceleration. Cool, that's a legit equation. And then we want to know change in velocity is acceleration change in time. So there you go. We have three equations, and what are we trying to find? We're trying to find that velocity after we accelerate for 5 seconds. So we're going to start with a velocity of 0, and we want to know our change in velocity, which is just the velocity after 5 seconds. So we use this equation. Change in velocity is 5 meters per second per, 1 second. Kind of a fancy way to write acceleration, but it shows your change in velocity for that unit of time. And then we're going to say 5 seconds. So heck yeah, it's just 25. 25 meters per second. That's going to be our velocity right there. And the same thing happens on the way down. We're just going to decrease. So our acceleration on the way down becomes negative 5 meters per second. So our change in velocity goes from 25 minus 25 meters per second. So we go from 25 meters per second to 0 meters per second when we decelerate. Okay, heck yeah. So, and now we just have a constant speed of 25 meters per second. So now when we do this to find, or just to see if this works, we're already choosing our time uniform to be 15 seconds across here. Now just from this, we just want to know what our average velocity is. So our average velocity is the time for it's the total distance divided by the total time. You know what I mean? So that's a good representation of velocity, of average velocity. You know what I mean? If I see you here, but anyway. So and for this one, the area under the curve is kind of fascinating. The area under these curves are the distances. You know what I mean? So the distance total, just from visually that, is kind of a fun way to do it. And then why is that? It's because this line, this height of this line is in meters per second. Meters per second, that's this unit. And if we multiply by seconds, well, heck yeah, we get distance in meters. You know what I mean? So it's the same thing as saying, hey, I have a square that's 1 meter by 1 meter. What's the area? Well, it's going to be 1 meter squared. But now let's say I have a square that's 1 meter per second on that side, and then 1 second on this side. Well, I'm going to go 1 second times 1 meter per second, and I'm going to get 1 meter. So that's going to be the area of that square. You know what I mean? Just two different things that you're representing. Okay, so 25, but the area of a triangle isn't just... Alright, that's a bummer. Well, my SD card ran out of juice, and we lost about a minute, but that's about it. So what we were going for is like, hey, we're trying to find the area of this triangle, is the distance, but it's not just height times base, it's a triangle. So you can take this side times this side, but then you got to divide by 2. So it's not that area, it's the area of the whole square, but half of it. So, and then we did that. So we did 25 times 5, and then divide by 2. So for this 5 seconds, we went 62.5 meters. And the same for this one. We go 62.5. Now the middle section, we're going to go 25 is our height of our velocity, times our seconds is 15. And this is the distance, 375 meters. So then it is cool because our total distance is just going to add up these, 62.5 plus 375 plus 62.5. And we get 500 meters, and then our total time for that is 25 seconds. And then hell yeah, you know what I mean? We booyah. 20 meters per second is our average velocity for that scenario. And that was the average velocity that they were saying in the problem. So now we have our answer. The time, how long does the car move uniformly? Well, it's going to be 15 seconds. So, heck yes. So now what we're going to do is like, well, cool, we got there, and we didn't even get there using equations. We got there from like a guess and check perspective. We said, back to like, well, what if you're just going that velocity, for the entire time, and then your acceleration and deceleration is just almost instant. Well, then yeah, you are going 20 meters per second for this entire time. But let's do the check on reality. But we know that's not the case. You're going to slowly increase to a speed, and if you do that, and our average velocity is still 20 meters per second, well, our top speed has to be greater than 20 meters per second. Is that what we find? Heck yeah, our top speed is greater. It's 25 meters per second. So, and so that's a good check on reality there. So now what we're going to do is and it's how we started this problem. It's just like, hey, get some numbers to it, and then we're going to see what we did to those numbers to get equations for things, and then we're going to see if we can just use it with letters. So let me maybe print out some more sheets of paper. All right, hell yeah. So and then we're going to get an equation for how we got there. And we're also going to get an equation with just letters. Just with they're saying the acceleration is going to be this letter omega. I can live with that. And we have a velocity of just v. Cool, I can live with that too. Now, when we get an equation with just letters, it's almost useless because it will only apply to the situation where we accelerate, which takes a certain amount of time, go uniformly, and then decelerate. So it's only for that scenario. It's not going to be like you can't do that a couple times and then come back down. So our equation, it will just be specific to this problem. But when you get an equation with letters, then you can at least change the acceleration. You'd be like, well, let's say if I have a super fast car, how is that going to change that time uniformly? So, what we're going to find is that we're going to have a time, I'm just going to say time u, tu, that's going to be the time uniform, and now we're going to have an equation, So, and then it's going to be, we're going to put our input parameters. So it's just kind of interesting how equations work. You might see this, where we're going to have time uniform as a function of t total. And I guess t total is just going to be t. I guess that's what we're going to call t. That's what they label it here. So we're going to have t uniform as a function of the total time, is a function of the acceleration. And these are all things that we can change. That's why they're functions of it. We can change the acceleration. We can change the total time. And it's a function of, and I guess I will use this, just for the book. But that's why it's like I don't like to use these symbols off the bat because I'm not used to them. But now that I know that I'm confident in how the problem works, sure, I don't mind using them. So now this is our equation, And this is no different than having, if this is our equation for x, and this would be y is equal to x. Well, this is the same thing as saying y is a function of x, and that's x, because, hey, look, like it's and this is where you can get kind of creative and be like, well, this is also, y is a function of x and time. Well, it's like, it doesn't look like it is, but hey, it's just x t to the 0. So, you input any time parameter in here, well, you're just going to have like 50 seconds to the 0. That just becomes 1 and becomes, a non-factor. So it's just kind of fascinating. And I use this. I don't know if I'm using this like in a wrong or bad way, but I don't think so. I think, and it's very useful for when you integrate, based on time, because you're just like, well, there is no time component there. But you'll have like if you do integrate y of x, dt, that's going to be integration of x dt, and I don't want to get into that. But anyway, so this is what we're going to do, and we're going to get an equation of time uniform as a function of those parameters. Those are the only input parameters I see. And we're gonna, the first thing that pops up is obviously we're gonna have a time to accelerate, a time uniform, and a time to decelerate. And we're gonna call this time uniform and this total time. So if we did wanted to find, if we're calling this like t acceleration, those two time frames are going to be the same. So if we call this t acceleration and this t acceleration prime because we're decelerating, we could say t acceleration is equal to t acceleration prime. Now this is also a skill that, you know, the MIT professor, if you watch those videos, they're just like, heck yeah, choose your own variables and have them make sense to you. Don't just caught up into other variables that, like letter-wise, what people use, because you're going to come up with your own equations in your own way that makes sense to you. And it's just good to know that, sure, these two times are the same, but they represent kind of two different things. This is the time to accelerate, this is the time to decelerate, and that's where that prime comes from. It'd be like prime is decelerate. Cool. So those two things are going to be the same. And for those zones, the total time for that period is going to be, well, the total time minus the time uniform. This is going to be total time accelerating, you know, or decelerating. You know what I mean? So now we kind of have an understanding of the problem from that perspective. But because we have a uniform situation, that's why I said it's just like, well, yeah, we're going to get a very specific case where we accelerate for a certain amount of time and then decelerate. But that's exactly what has to happen if we have a uniform acceleration and uniform deceleration. Or I should say that that the acceleration is always the same, you know what I mean? So I mean, because this problem could be different. We could have, from using this a and this a prime, we could have a function uniform of the total time, the acceleration to accelerate, the acceleration prime to decelerate, and the average velocity. You know what I mean? This is a problem that I could do. After solving this problem, I could come up with my own problem and get an equation for this. You know what I mean? Yeah. I just have to spend another 4 hours on it. Cool. So let's see where we're going to go from here. Yeah, we should probably just get to it. We have those equations for acceleration that is change in velocity, change in time, and again we have access to all, you know, 4 combinations of this. You know what I mean? Which is very useful. You know what I mean? So we have 3 different equations here, just rearranging, because that can be very useful. And then even with velocity, what the hell is velocity? Well, it's distance divided by time. And right here we got 3 equations. We could say time is equal to distance divided by velocity, and distance is velocity times time. So even just right there, we have 3 equations that are very useful. And because how we got, and then we have our equation for what is average velocity. Average velocity is the distance total divided by the time total. And you might just want to know the average velocity from there to there. You know what I mean? Well, it's going to be the distance from there to there. That's going to be that total distance. And then it's going to be the time from there to there. You know what I mean? That's going to give us the average velocity during that time frame. So even if I just have a very short time frame, like pick this one, the average velocity for this time frame is going to be the distance I travel divided by that time. And we already found out that the area under this curve, because this is a velocity time graph. We have time, positive time in this x coordinate, and then this in the y is meters per second velocity. And so what is this velocity? You know what I mean? So, well, we know from the acceleration equation that velocity is going to be the acceleration times the change in time. So we know the velocity up here, and that's just going to be v. That velocity is the acceleration, which we're calling w. And is that omega or just w? Hard to tell. I'm going to say omega for that because I'm used to saying omega. And then the change in time is just the time for acceleration. Cool, and that's going to be the velocity component there. And then for our problem, we know what that velocity is. That's going to be 5 meters per second squared times a time, or maybe we don't. Maybe we don't know what that time is. So we're just going to say TA. But that's going to be our velocity right there. Now our distance, we already said that that's going to be the area under the curve. So the distance that we travel for that first segment, I'm just going to say like distance for that first segment, D1, is, well, it's going to be the velocity, that velocity, divided by, or what is the distance? Distance equates, even right here, it's velocity times time. So it's going to be that velocity times that time. Oh, weird. Oh, yeah. No, duh. Yeah, it's velocity times that time, TA. Oh, this is tripping me out. I always forget that distance is like you're using that time component twice. One, you're using this time component to figure out the velocity. If you know the acceleration, you take 5 meters per second times 5 seconds, and then you get 25, meters per second. So, using some numbers on this makes sense. And then if you wanted to know the distance, well, you're going to take that same 25 meters per second times 5 seconds, and then half that. So that's fascinating too. So the distance is going to be, hey, that velocity times, and then divide by 2. It's the area under that curve, and and we gotta take a step back, because if we're gonna point out everything, because this comes up all the time, is your velocity here is 0. And then you get some max velocity, V max. But now we want to know what the average velocity was, because you can't just say, if I go from 0 and increase my speed linearly to some sort of max velocity, and over a period of time, and this is where it's just very important to go back to going from 0 miles per hour to 60 miles per hour over the course of an hour. It's a bizarre one, but you could visualize it. In your car, you're going 0, slowly increasing to 60 miles. And this does not mean that you went 60 miles per hour for 1 hour and went 60 miles. That's just not the case. You know that here you're going slower you're only going 60 at the very last part of the trip. And so you need to know that, hey, there is a velocity average, and it's 0 plus 60 divided by 2, and we went 30 miles per hour. And so that's going to be the average velocity. And only when you get that average velocity times that time, velocity times time is distance. Cool. So, yeah, so even here, maybe I should put this an average sign. Average velocity is distance divided by time. Because in these problems, you're going to have like a linear relationship where you have 0 velocity, and then you have a max velocity, and then you want to know how far you went. Well, you have to take the velocity average. That's the integration approach. And so that's where this 1/2 comes from. And then so we have the distance at 1 is v times this time for that little section divided by 2. We know that v is equal to omega ta. So, and then that's where this time gets squared. Because see how v is equal to omega ta. We're going to throw that right in there, and then we're going to have another ta, this time for acceleration. So our distance is going to be 1/2 the acceleration time squared. Cool. And you know what I mean? We might as well use this problem to kind of explain everything, because you have this idea that acceleration is change in velocity, change in time. It's dv dt. And if it is dv dt, then you can rearrange. You can solve for velocity and or dv, the derivative of the velocity, and then integrate. So you're going to take dt and put it up there, and you're going to have dv is equal to a dt, and now you can integrate. You know what I mean? And so this is where we do it. You get velocity is equal to acceleration times time plus a constant. And all this constant says, hey, what's your velocity at time equals 0? Well, my velocity is 0 at time equals 0. So this constant has to be 0. And now you have an equation for velocity. As a function of time is acceleration times time. And then we can say, hey, and this is one that I haven't done yet, is like, well, I kind of did with d over t, but usually I don't do velocity like distance divided by time. I say velocity is change in x divided by change in time, because physics books always start with linear velocity from 0 to x is equal to something, and it must, your time is 0 right here, and if you got over here, your time has to be something. Let's say 1 second. And this is a fundamental of mass. This is Newtonian perspective on, like, if you have a mass and then you visibly see it here at a time and then you visibly see it here at some other time, well, it must have had a velocity. You know what I mean? That's the definition of velocity, is that it changed its position, change in x, and over the course of some change in time. Now, this is Newtonian mechanics because you might see a particle of mass here, and you might also see that same particle of mass over here at the same exact time. You know what I mean? So this particle of mass does not obey Newtonian mechanics. It doesn't. It can occupy two places at the same time, per se. Or it can be either there if you observe it there, or it can be either there if you observe it there. If you take that, so only in Newtonian mechanics says if you see someone at the grocery store, right when you get off work, but then later that evening you see them at the bar, well, they must have had velocity because they changed their position and there was a change in time. And so that's the definition. They had to have velocity. There's no way you can, time warp, in no time from one place to another. And so the Newtonian mechanics say, hey, you're made of mass, and if I identify that mass in two different spots, well, there probably had to have been two different times to observe the same mass in two different spots. You know what I mean? Okay, cool. But that's where this equation for velocity comes from. And now it's the same thing. Velocity is dx dt. And then we can get an equation for position. Bring the dt over here, and you're going to get v dt is equal to dx. And now you're going to integrate. Did I do that right? Yeah. So we're going to just bring the dx on one side, and then you're going to have v dt. Well, we know what the equation for v is. And so we're basically saying this. If this is our equation, we're going to say change in position, change in time is equal to acceleration times time. We're going to take the dt over here, and then we're going to integrate on position. So we're going to get an equation for x as a function of time, and we're going to integrate acceleration aat dt. And when we do this, we're going to go a to the t. This is t to the 1, so we're going to go t to the 1 plus 1 divided by 1 plus 1. So we get t to the t squared divided by 2, and now we have a constant. And the constant says at time, and let's do this one more time. It's 1/2 acceleration times squared, and we're saying when time plus a constant, when time is 0, what's our position? And we're going to be like, hey, our position x is 0. It's 0 right there. So that's where that comes from. But you can see how if all you do is just have this little scenario in your head, that if I have 0 velocity and then go up to some velocity, well, the average is just halfway between those two for that time frame. So at time 0, we're going to have 0 position. So our position, our constant is 0. Because when we throw time 0 here, we get 0 on this side, and our position is 0. Same thing with that velocity, this one. If this is our equation for velocity at time is equal to 0, our velocity is equal to 0, so 0 is equal to 0 plus constant. Constant has to be equal to 0. So now we have this equation for position, which was identical to what we just did. Our equation for position x or d, for that time frame is 1/2 acceleration t squared. Hell yeah. All right, but those are the things that people aren't just going to spout out. That's why you have are they called kinematic equations? Where you already just have this spelled out for you, where you have position. If you did have some sort of velocity in this one, if you throw in time 0 and you did have some sort of v initial, then when you integrated, you would have v initial t. You know what I mean? And then let's say you had some sort of, at t is equal to 0, you did have some sort of initial position, not at 0. So then your kinematic equation says that position is 1/2 acceleration t squared plus v initial t plus x initial. But the fact that you would just look this up and use it is criminal to your paying big bucks in education. You know what I mean? The fact that I had to go through first year college physics and they're just like, yeah, just use that equation. It's just like, no, just teach me the integration or teach me this. All right, hell yeah. So I think we're on the home stretch, and it's just fascinating. You know what I mean? I think this is, if I get it right, it's kinematics. So there's two different things here. You got kinematics and kinetics. And there's nothing more fascinating than taking a textbook after, you've either done the course or came back to it, and then just read the first chapter. I mean, it's like this, especially this dynamics book. It has an introduction, just to hear. But just within a paragraph or two, it literally gives you exactly what's happening with dynamics, the limitations. So this is rigid body dynamics, how you first start with a particle, and just, with no mass, no size, and then figure out the velocity and motion of it. And then you have this idea of kinematics, is the study of geometry of motion. It's not concerned with what causes motion. So we're not concerned with the mass of the object. Kinematics is like, hey, let's just talk about a particle moving. So that's what we're doing in here. We're talking about the car as a particle. We don't care what's moving it. We're just saying we don't care that it has mass, and we don't care what's moving it. We're just observing motion. And so that's kinematics. It's the geometry of motion. But kinetics, on the other hand, that's where we get into F equals ma. And I don't know how the hell you would actually remember that, but your kinematic equations, suck. You know what I mean? When you get them in this is a kinematic equation. And if you have them like this, you're never going to remember those. But then kinetics is the F equals ma. So let's continue on from there. And during the break that I took, I definitely wanted to point out, was like, well, isn't this a kinematic equation? You know what I mean? And it is. When we're talking about velocity, like when we do those road trips where we're just like, didn't we go on a road trip that we were just going 60 miles an hour for an hour? You know what I mean? So that's what that is. So when we do that, we're just saying acceleration is 0. We're not changing our velocity. We're just going 60 miles per hour. It's just that location. So for this period of just going like, let's say 60 miles per hour for an hour, we're going to be going 60 miles. So wouldn't this kinematic equation give us that? Because we're going to throw a time in, of 1 hour, and we're going to have a velocity of 60 miles per hour. And sure, because we're going to start with a position at 0. That's going to be at the stop sign of whatever town we're leaving. And so that's going to be 0. Our acceleration is 0 because we're not going to change velocity. We're just going to go 60 miles per hour for our entire trip. That's become 0. And look at that. You know what I mean? We have distance is equal to velocity times time. Distance is equal to velocity times time. So it's just fascinating how that these are kinematic equations, so it's just, that fascinates me. All right, because even this acceleration, it's the change in velocity, but nothing else. It doesn't, because let's go back to our velocity equation. Can we do this one from scratch? Well, that's going to be acceleration times time plus the constant, and what's the constant on isn't that just velocity initial? Well, yeah. But when we talk about acceleration, sometimes it's just easier to talk about when we don't have any initial velocity, And then we get this. Velocity is acceleration times time. Well, isn't that, yeah, velocity is acceleration times time. Yeah, so that's that equation, just with no initial velocity. Sometimes all you want to do is find the change in velocity and just have that parameter in your head. Like, obviously, you're going to do the work and be like, well, if I'm starting at 0, cool, my change in velocity is just, we're going to go from 0 to 25 meters per second, because my acceleration is 5 meters per second for every 1 second. Now, let's say I was just going 5 meters per second, like 10 miles an hour, and then I'm going to increase, for 5 seconds, I'm going to change my velocity by 5 meters per second every second. Well, then I'm going to be going 30 meters per second. And my acceleration is still the same. I'm accelerating by 5 meters per second for 5 seconds. This part is going to be a change in velocity of 25 meters per second. But yeah, it's just very intuitive that I'm already going 5 meters per second. It seems like you don't need a kinematic equation. The second these kinematic equations get proposed like this, they just look too complicated. You know what I mean? And it's just like, I don't know what all to put in. So how I do it is just go from the definition of acceleration, and get that. The definition of velocity, and get that. And even we did it from just like, it was very useful for these problems, these basic problems, just to say, hey, it's just distance divided by time. Like, average velocity is total distance, total time. That is very useful for me. And then also just knowing that, hey, we have units on velocity of meters per second. We have units on distance of meters, and we have units on time of seconds. These 3 parameters are related, and you can relate them any way you want. Meters per second times seconds, seconds cancel, you get meters. Meters divided by second, you get that parameter. And then meters divided by velocity. Well, meters cancel and seconds pops upstairs. That's the exciting one that I like to use. All right, so it's fascinating that you can use kinematic equations, but they're ugly, complex, and I only like to pull them out for when you are going to have, I don't know, projectile problems. That's where you definitely want to start out with your acceleration, integrate for your velocity equation, and then integrate for your position equation. Okay, so we're almost there, but that thing totally spelled out why. Whoa, we had an equation for velocity that was going back to the kinematic equation. What's the equation for velocity? Well, it's the acceleration times the time. 5 meters per second every 5 seconds. And our initial velocity was 0. So that is where we got this velocity. And you could even add, this plus velocity initial, but that's 0. So that's the kinematic equation right there. We just got this equation just from the definition of acceleration and knowing that we have 3 terms here, and you can rearrange, for kind of 3 different equations. And then we just said, well, what is our change in velocity? And our change in velocity starting at 0, well, that was just obvious to see that is our velocity at that point. But then we ran into the hiccup that the distance wasn't so obvious. Because, cool, we had a max velocity here, but we started from 0. So over this time frame, you have to take your average velocity. That's the only way that you're going to find the distance for that time frame. It's the area under the curve, or just the average velocity, and that's when, yeah, sure, the kinematic equations are kind of useful, because you have this 1/2 omega t squared term, and that's going to be our distance for that segment. All right, so the distance for the second segment, based on all that jazz, was like, well, you don't have any acceleration for the second segment. So the second segment will just be that V max times the time, and then you could just say the position right here is 0, 2 if we just wanted the distance for this second time. You know what I mean? So that's using the kinematic equations, just for that. And you get that the distance for that second is just going to be, and then you can just go back to here. What the hell is distance? It's just velocity times time. It's that V max, or just, and we're calling this V for our problem. So that's V times the T naught. So this is going to be or no, TU, I'm sorry. So that's going to be time times TU. That's going to be that reference point. And for to get this problem on the road, we're going to have symmetry here so that section 3 is just going to be the same. It's going to be 1/2 omega, and then here it needs to be t acceleration. So it's the time for that acceleration. So we're going to have the same thing, time for acceleration squared, and we already said that the time for acceleration to accelerate is the same for time to decelerate. Even though we're decelerating, though, we're still having an average velocity in that direction. So we are decelerating, but we're still going this direction. If we decelerated enough, well, yeah, maybe we're going the opposite way. You know what I mean? We're going to change our velocity and at some point start going the other way. But in our problem, we're starting from stop, getting up to a speed, and then going back to stop. Okay, so I'm going to take a pause, and we're going to kind of clean this up because we actually need to get to that equation, this equation. So catch you on the flip side. All right, hell yeah. This is really cool because this is exactly the teaching method that I'd want to teach kinematics, you know what I mean? Because it's just the obvious, like, hey, what is velocity? You know, we have units on velocity, meters per second, distance, time. And so how do we rearrange these? Well, we say that velocity is equal to meters divided by seconds. So that's what we get. We get an equation. We can rearrange 3 different ways. We can bring the t up there, bring the v downstairs. For here, the t just goes upstairs and you get v. And then we can say the same thing for acceleration. Acceleration is change in velocity, change in time. And even these could be velocity is change in distance, change in time, because we definitely have these 2 equations that represent acceleration is change in velocity, change in time. Velocity is change in position, change in time. For this problem, omega is going to be used for the acceleration. You know what I mean? Sometimes I wouldn't use that. I would just say A, but we're going to carry that through. So now we have change in velocity is, for our problem, is just going to be omega times t. That's what we had, 5 seconds, and then we got up to 25 meters per second in that 5 seconds because our acceleration is 5 meters per second per second. And then our change in position, that was an interesting one because we had to take this change in velocity and then put it into here. And then so it's the acceleration times time, and then multiplied by time again. But that's not the equation for distance. We have to realize that the only reason why you can do this is your change in velocity is because your acceleration is constant. And this is why, anytime you're doing a gravity problem, yeah, acceleration is just 9.8 or 10 meters per second per second. And so that's going to be a constant, and then so every second, yeah, you're going to be going from 0 to 10 to 20, you know what I mean? Where the second you start getting into, the second your velocity starts changing, well then your position is going to be different, because then it's the same scenario where you have this car going 0 to 60 miles per hour. I know it's bizarre, but over the course of an hour, you have to take the average velocity. Velocity average is 30 miles per hour. So just visually, you have to, remember that and understand that. And so that's where this problem says, hey, our velocity initial is 0, and we're going up to some velocity. So the kinematic equations take care of that, because once you integrate, because here they are, you're taking this acceleration, which is dv dt, rearranging, and it is a constant, and then so you're getting acceleration times time is velocity plus velocity initial, and then integrating again, and then you get that 1/2. Your change in position is essentially 1/2 the acceleration times time. And the reason for that is because you had 0 velocity here. Your velocity here was the acceleration times time. And then your average velocity is, your velocity average is going to be acceleration times time divided by 2. And then you're going to take that value. If this is our velocity, how do we find distance? You multiply by time again. So then you take this and then multiply by time. So you're going to have omega t divided by 2. Visually, that's the average velocity, and then multiply by time again. So that's where this term comes into play. And yeah. Oh, and sorry, there should be a squared here. My apologies. But that's where terms like this get confusing, because this happens a lot in physics. Because over here, well, this term more representative would be omega t, you know what I mean, then divided by 2, and then times t, you know what I mean. So this kind of spells out the 3 processes that you're doing. You know, the fact that you just then say it's 1/2 omega t squared, well, a lot gets lost in translation. Now visually, this doesn't look familiar to me at all. You know, I just know that it's a kinematic equation, but from here I don't see that, oh yeah, the velocity, the acceleration was the acceleration times time. That was going to be my change in velocity, but I already started with a velocity of 0 and I got up to that. So my average velocity is divided by 2, and then if I know that average velocity, I know the next equation for distance is average velocity times time. So I'm going to do that again. And that's the simplest scenario where you're starting from 0 and going up, where you have an initial velocity of 0, you have an initial position of 0. Cool. So, I think we should be starting to, solve this problem using those symbols. But we don't have to use the that's the fascinating thing. It's like even the symbols get confusing for me, that it makes more sense to kind of throw in those values. But that was the wild one. It's just like, well, how did I get the velocity up here? Well, I took that acceleration, 5 meters per second, multiplied by the time of 5 seconds, and then that was the velocity, divided by 2 to get the average velocity, and then multiplied by time again, 5 seconds. So like, whoa, that's exactly that equation. And that's the only way that I actually got that velocity up here in the first place. And then once I know that velocity, no. This was the distance, you know what I mean? This was the equation for that distance. And then I can say, once I know that velocity, this next distance is going to be 25 meters per second, or it's that 5 meters per second squared times that 5 seconds, that initial 5 seconds to get up to that speed. But now we're going to take that velocity and then multiply it by TU, which we know is to be 15 seconds. So that's going to be TU is equal to 15 seconds. But right here, here's my TU term. And then this again was my omega t, my acceleration times time. So if we throw the values on, and the whole thing is just to get total distance. Because, to take it full circle, they wanted to know if the average velocity was this. We need an equation for the average velocity. And the easiest one is total distance divided by total time. Because that's like, hey, if I see you at the grocery store, and then 2 hours later I see you down at the bar, I know your average velocity. We know that you got into a car and then went real fast. We know that you walked to the parking lot and then went home and then just stayed there for a while and then drove real fast to the bar and then walked to the parking lot. You have real high peaks in velocity. Every time you drove, you had high peaks in velocity. You had 0 velocity when you just chilled at home, and then you had very little, just tiny velocities walking in the parking lot. But if I wanted to know the average velocity, at no point, and let's say you were always constantly getting to, like, at no point did you go back to the grocery store to return something. You were always, your home is over here and the bar is over there. You were always trying to get to the bar, and so we can draw a line through here that says what's your average velocity for that time. And the easiest way to do that is say, hey, there's a distance between the grocery store and the bar, and there's just a time. This was time 0 when I saw you, and then time 2 hours later is right there. So if the distance between the grocery store and the bar is, let's make it 10 miles, and you kind of live in a big town, then I know that your average velocity was 10 miles, in 2 hours. So it's very fascinating that your average velocity was, oh, no, am I doing this right? Yeah, you went 10 miles, from the grocery store to that bar. This is a bizarre one. This is messing with my mind, but, that's a distance of 10 miles, and it took you 2 hours to go 10 miles. So let's say in 1 hour you went 5 miles. You're going 5 miles an hour, but it's just bizarre even just using these equations. It's just like, well, that's wild. If I see you at the bar, like your average velocity was 5 miles an hour. Like if you just walked to that bar, that's how long it would take you to get there. But we know we have cars, and we know that we have chill time at home, and you can still get to that bar 2 hours later. And we know that it was very important that your driving in the car was way faster, especially, because you can't walk through the parking lot 5 miles an hour. People will stare at you. That's really cool. That's really cool. All right, booyah. So we can bring it home, because this at the end of this was it. This was 72 kilometers per hour was our average velocity. And what's the equation for average velocity? Well, it's total distance divided by total time. And they even give you the total time. It's 25 seconds. And we can do that in hours. That's just going to be 1 hour, 3,600 seconds. And then seconds cancels, that's the time in hours. And then we're going to find the time in distance. And we can do this in meters. So obviously this is going to be 72,000 meters per 1 hour. And this is going to be our average velocity. And then so when we plug this in, we're going to have variables in here, but it has to equal this. You know what I mean? So even right here, this is 25 divided by 3,600. This is a very short amount of time. And so even from right here, we have three things. We have this is equal to the distance total divided by 0.0069 hours. How would we get distance total? We're going to multiply these two. We're going to bring that upstairs. So times 72,000. So our distance total has to be 500 meters. So even right there, that fascinates me. That I didn't know that right off the bat. That was not spelled out. But after going through this whole process and knowing that velocity average is total distance divided by total time, well, it's already given me those. It says, hey, well, this is three things in an equation. I can solve for total distance. That's velocity average times total time, and that's going to be 72,000 meters per 1 hour. Times that time of 25 seconds divided by 3,600 seconds, and that's the time in hours. And then we just did it, and we're going to go 500 meters. And then so this equation, so we go back to this equation that we've been starting on, is our total distance. And it's that kinematic equation. Well, to get the distance for this first part, we need to know our velocity initial, our velocity after we accelerate, and we know that we have an average velocity in there over the course of that time. So this is our velocity max, and then divided by 2 is our velocity average times that distance. And it's the same thing. This is omega t, and then so the area of that circle, the area is going to be this height in omega t times this time in ta, or just another t. And then divided by 2 because it's a triangle. It's not a square. But then for this one, we have that we have a square. So we have that total velocity, which is going to be v, and then we're going to multiply it by this tu. You know what I mean? And then on the way down, it's going to be the same thing. Kinematics say we're going to decelerate, and so our acceleration is going to be negative 5 meters per second And so kinematics says that, and we know we have the time frame on this, so we can find our velocity final. So let's do this. So here's our equation for kinematics. Our velocity is going to be omega t plus velocity initial. But here we do have a velocity initial. From our initial thing, our velocity initial was omega t. And let's do this right, because our new time frame is ta prime. That's the deceleration. So our velocity of that time is omega ta prime plus velocity initial. Well, we know velocity initial from that first kinematics was 1/2 omega ta squared. And so there you go. And so you're going to have velocity for that time frame is going to be omega, and it's going to be we're going to say this is omega prime, you know what I mean, because it's negative. So we're going to have omega prime ta prime plus, and then 1/2 omega ta squared. And whoa. That wasn't our velocity for our velocity initial is just omega ta. Sorry about that. So this velocity right here was omega ta, and then so we're going to have omega ta prime plus omega ta. And this should give us the velocity at that ta prime. That's what we're trying to find. This equation was basically saying acceleration t plus velocity initial. Well, we knew our velocity initial, and now we want to find the velocity at this new time, at ta prime. And heck yeah, we're going to get omega prime ta prime plus omega ta. And that's what we're doing. We're using letters that are just like, all right, my brain can't handle it. But this omega is negative 5 meters per second, and the time frame on this, well, let's say we don't know it, but we do know that the time for acceleration is the same for time to decelerate, and so I mean, I guess we do know it. You know what I mean? Let's just throw in that 5 seconds, and now we got plus 5 meters per second times 5 seconds. So you can easily see that this was negative. Negative 5 times 5 plus 5 times 5. So this is going to be 0. So our velocity at the end of that time frame is going to be 0. So that's kind of what that showed. As long as our acceleration was equal and opposite, we had positive 5 here and an acceleration of negative 5. Then we're going to start at 0, get up to speed linear, and then go down to back to 0. But yeah, for whatever reason, that kind of sucked. But what's our distance? Our distance is, can we use the kinematic equations for that? Holy hell, it's like I don't even want to. But yeah, let's start getting kind of this. Yeah, because I'm fascinated with this is why letters suck, and it's just easier just to throw in an example at it that makes sense. So we're trying to find this distance, and so that distance x is a function of t. We're going to have x as a function of t is 1/2 omega prime, because now we're decelerating, our t value, which is going to be ta prime, and then we're going to square that plus our initial velocity. So now we can go back. Well, that was that first equation. That was going to be omega ta. But now we're going to have to multiply that by ta prime. Cool. And then plus our initial position. And we're just going to say x is 0 there. You know what I mean? All we want to know is the distance from there to there. And we have this relationship that ta prime is equal to ta. And we're going to say that's equal to 5 seconds. Omega naught is equal to negative 5 meters per second. Omega is equal to 5 meters per second. Change in velocity of 5 meters per second every 1 second. And then and that should cover it. So now this position from there to there, the distance, using these kinematic equations that are just painful, is 1/2 negative 5 meters per second times 5 seconds squared plus 5 meters per second times, and these times are the same, so we'll just do 5 seconds squared. Cool. So now what we have here is, let's do this one first. 5 times 5 squared is 125 meters, but then we have to subtract. This is 0.5 times -5 times 5 squared, and we're going to subtract 62.5 meters. So now we got 125 minus 62.5, and we get a total distance for that using the kinematic equations of 62.5 meters. But yeah, there's so many opportunities for the kinematic equations, one, to not make any sense, and like what are we actually throwing in there? And it's just way easier to just, throw numbers at it, know your speed, and then, hey, know what your speed is changing, find the average velocities, and then over that time frame is going to be your distance. Okay, so we basically did it, and we're going to say that this omega prime is the same thing as omega. We're going to say TA prime is the same thing as TA. So when we go to actually get this whole equation in here, all right, I probably said home stretch 30 minutes ago, but heck yeah. So we're gonna get this final equation. So we have v prime, or the average velocity is distance total divided by time total, and we know that input parameter. We know that input parameter, and so we're gonna have something where we're gonna have a lot of stuff, and then tu, and that's gonna be an important property to us, and we're gonna have to solve for tu. And actually, it's so fascinating, the fact that I just guessed this, use those strategies to guess the answer right. I know that I have two different things. I have this TA, which I do not know, and I have this TU, which I do not know. So right now, I'm bummed out because I don't just have one equation, one unknown. When I throw this together, I'm going to have two things that I don't know. This time uniform, and then also this time to accelerate. And so there is going to be a continuity there. And I swear, it's like my mind is totally mush, where it's just like I don't see it. I don't see the magic trick that links those two together. Okay, so let's do this. So we have the distance is going to be omega. Alright, so my camera overheated, and this is my current strategy to do the problem with numbers, get the right answer, and then come back with letters, and even if it just looks kind of horrendous. So we're typing all this in. So from the kinematic equation, we know that distance is going to be that acceleration times that time. And I'm just going to say this TA is equal to TA prime is equal to just T. So we're just going to call that T, but TU is what we're mainly interested in. So we don't know T and we don't know TU. But we do know that oh my God, see, this is the fascinating thing where I just don't see it. It's like your brain is just mush. You know a lot, but then problems come down to like a continuity. You know what I mean? Like, and so the continuity here is that the time total, because that's part of the equation. They're just giving it as, that's why I kind of sidestepped, is 25 seconds. But the equation for time total is time u plus 2 times that time t, you know what I mean? And we're saying that time t is that time ta is equal to time a prime. And I really like setting this up with the a and the a prime, with the acceleration on the way going faster is omega, and then the acceleration prime is the deceleration part. This is the positive, because then I can know the fundamentals, so I could change these parameters, you know what I mean? But you would still, I mean, we're gonna get an equation now with just TU, and the only reason we're gonna get an equation with TU is because we know the time total, and we know. So let's go over this again. If time total is equal to TU plus 2 times T. Like what we want to have our parameter be is this. This is the only unknown that we want. And so we could say anytime that we get this value, Well, we can just solve for it. So what we're going to do is we're going to do t total minus tu. So we just brought that over here. That's going to be equal to 2 times t. Okay, now we're going to take, we just want to solve for that t, and we're going to divide by 2. So cool, we're going to have t total minus tu divided by 2. So now we have an equation for this interim time, this time to accelerate. The time to accelerate is, well, it's the, and it just makes sense. It's the total time minus the time of uniform, and then divide by 2 because there's 2 of them. So now anywhere in the equation where we have time to accelerate, like right here, we're going to throw this in. You know what I mean? And just, you're not going to be able to do that right off the bat. So that's where, you know, like one of the commenters a long time ago, you know what I mean, and hopefully people more comment this, it's just classic. It's just like, oh, you need to solve the problem with letters the entire way. Well, you know, let's get back to where we actually started with this, with our little juggler people. What are we, 5 pages in? You know what I mean? This is like, you know, there's some days where my mind is just a total garbage pit of mush, you know what I mean, where I can only juggle one thing. And that's why it's just like, hey, I'm just going to go through the entire dictionary of my brain of what I do know, and then hopefully it mimics the problem of, like, you know, getting that solution. Sometimes you can juggle 2 things. Sometimes you can juggle 3, and you can just go right for the letters right off the bat. Where, you know, you would be like, well, the velocity average is obviously the distance total divided by distance time. And then you would say, well, that's going to be the acceleration. During this time of acceleration, well, it's just like, oh, hell yeah, I obviously know that. That's going to be the total time minus the time uniform divided by 2. There's absolutely no way I'd be able to do that. Right now, it makes sense. And this is an important aspect that I'm going to put more emphasis on at the end of my problem. Solving them with numbers, solving them with kind of like this this ability just to, hey, turn it into cars and speed. If that's the case, make them simpler. And then at the end, throw in the letters. Because if I had a textbook that just said this, you know, now I can have an understanding of where that's coming from. I mean, because, you know, some of these problems might be solved in that way. They're just going to go right for the actual answer, and you would spend a lifetime figuring out how they actually got that for that time acceleration part. But now, like, we can just do that right now. So over here we were going to say acceleration times time is that distance. I got to get some more time on the clock. Yeah, and it's so bizarre, the fact that, hey, this should be so easy. It's just the total distance and divided by the total time. And that's where we did set up relationships where it's just like, yeah, if I'm driving in a car, who cares about the time it took to get up to speed? All I want to know is just my average velocity in the car and kind of that time that I got to that next town. That's going to give us the distance. But this problem, no, you kind of have to buckle down, and that's why we use that idea of like, well, if we're going from 0 to that max speed, well, it's just the divided by 2. So yeah, because that's going to come in right now. We're going to find that velocity. This is the velocity for that time frame. But now we're going to find the average velocity, so we're going to divide by 2. And now we're going to multiply by the actual time frame again. You know what I mean? And again, TA is equal to TA prime is equal to T. So that T is what we're doing. So now we're going to multiply by T again. That's going to be that distance there. And so it's just fascinating that, you know, I didn't even notice that I can come down here and just say, well, this is 1/2, and then we're just going to square it. That's that distance, you know what I mean? So we're still on this upper part of the equation, and then at the end of the day, we're just going to all divide by that T total. T total is that 25 seconds, right there. Okay, so now we have, and since the problem is the same for the acceleration as deceleration, we can say, well, these distances are the same, and now we can just throw a 2 right here. We can just multiply by 2. You know what I mean? So that's going to be helpful in the end, and we could do that right here, and those are going to cancel. We have omega t squared. That's omega t squared. And now we just have this one. And so the velocity max is going to be that omega for that initial t, and that's going to be that, times this tu. So now we have times tu. this is going to be the distance. And let's do a check on reality, because a check on units. So we're going to have meters, and then we're going to have seconds squared for this acceleration term. And that's going to be confusing for this problem. Omega is acceleration. But this is why you do problems with letters, to get used to using whatever letters, whatever letters you make up at the beginning of the problem. That's what we're gonna, whatever they used in the problem, that's what we're gonna be using. But if this was a test, right away I'd be like, oh hell no, omega is acceleration, A. And I'm gonna call it A the entire way through, and then switch it back to omega. Okay, so check on reality, we have time right here, and then we have another time. So those 2 seconds cancel that, and we get distance. All right, so we got to check on reality there, and then we're good to go. And now we just divide by that time total. So cool. And down here it's going to be plus omega, and we're going to have this this t. The time to accelerate is t total minus tu divided by 2, and now we're going to multiply it by tu. Cool. And that's it. So even right here, we just want to check on reality that we haven't made any mistakes. So let's do it. We're going to go 0.5 times 5, and then this is going to be 25. And we have to throw this into our equation. Well, no, we've already figured out that TU is 15 seconds. So yeah. So we're going to go 0.5 times 5. 25 minus 15 divided by 2. Oh, I need more parentheses. No, I don't think I did. No, I definitely need another parentheses, because I got to square this. So there you go. So I got to square that term. And then we're going to go plus 5 times 25 minus 15 divided by 2. See, this I don't have to put more parentheses, because I basically just did that in parentheses, divide by 2, and now I can just multiply by 15, and that'll work in the calculator. And then we're going to divide by 25. And I get 17.5. What gives? Did I not do something right? Alright, so this time is going to be 25 minus 15 divided by 2. Yeah, that's the 5, and we're going to square it. We get 25 times 5. We had 2 of these. See, oh my gosh. Any time that you throw a different number, like higher or lower, throw some asterisks on the page, because you're going to make a mistake. So we can actually just go back to our equation. And I don't know if I put anything else in. There we go. And so we're going to go back to here, and instead of 1/2, we're just going to get rid of the half. Okay, heck yeah. And we get that distance of 500 divided by 25, and now we're good to go. So this equation jives, and I'm going to probably get some more paper going. And now we are on the home stretch. So we're cleaning up this equation to see if we can, but we actually haven't even solved. We just assumed that we knew the answer, but we actually have to solve for TU, so we're going to see how tricky that is. And I'm just assuming that I'm making these problems 1,000 times harder, but just in general, this book sucks, man. No, it's good, because it's just like, oh, this would make you want to quit physics, doing problems in this book. But anyway, we're learning tons, and we're learning how to juggle. Okay, so we have the acceleration, which is omega. We have t total minus tu divided by 2 squared plus omega t total minus tu divided by 2 times tu. And now this divided by t total, we can just say this is 1 divided by t total. I don't know if that's going to help. And now we have 1 divided by t total. So I don't know. That didn't seem to help. But we can factor out the omega. I don't know. What do you want to do? I just don't want to square this thing. You know what I mean? That's all. Holy, I didn't realize that this problem, and maybe I'm making this way too hard. I don't think so though. Okay, so we're just gonna square this term. So this is gonna be, and now I'm tired of writing TT, so I'm just gonna say, hey, T final is equal to T total is equal to T. You know what I mean? So now we can just write. So let's write it at least one more time, and we're gonna have 1 divided by T omega. Now we're gonna have T minus Tu divided by 2. We're going to square that plus omega T minus Tu divided by 2 times Tu divided by 1, and then 1 divided by T. Okay, so we need to square that term, so this is going to be 1/2 T minus 1/2 Tu, and we're going to square it. My way to square things is just square this term. So that's going to be 1/4 T squared. Square this term. I'm going to add it to 1/4 Tu. And then multiply. If we multiplied those together, we would get 1/4 T Tu. And then we're going to double it. So it'd be 2/4. So it'd be 1/2. So and there's a minus here. You know what I mean? So it's minus. So it's minus 1/2 T Tu. Oh, and then see, I'm making mistakes because this is 1/4 Tu squared. All right, and I don't even know. I mean, we're trying to solve for Tu. That was the whole deal, and yeah, because if you didn't want to do that, and you just got to this point right here, you could say you could do this. 0 is equal to negative. You could just bring this average velocity over here, and then then you could have plus. I'm just going to do omega divided by T, T minus Tu divided by 2 squared plus, and this is just omega divided by T. And then we're going to have T minus Tu squared times Tu. And so we can throw this into our calculator where this is the X term. This is the Y term. You know, anytime in your graphing calculator, your Y equals is this side. And then here's an X. And there you go. So now we can just type in the actual values. And we're going to for our time frame. Well, what do we need this to be? Well, we already found that 72. Okay, so we found that 72 kilometers per hour is going to be 72,000 meters per hour divided by 3,600 seconds in it. So this is going to be an average speed of 20 meters per second. We've done that. So this is going to be negative 20 plus this is going to be 5 divided by 25 times 25 minus x. Oh, and I need more parentheses here. Divided by 2, another parentheses, we're going to square that. Plus, we have 5 divided by 25. And then parentheses 25 minus x divided by 2. And so we're good there. And then multiplied by x. So even this trips me out. See how this says divided by 2x? Even in your calculator. So we did this 25 minus x in our calculator, and then we're going to divide by 2, so we did the divide sign by 2, and then we just put x right here. But the calculator is not going to put parentheses around there. It's going to divide this by 2, and then it's going to multiply up top this x. So it's just fascinating to get used to your calculator, because you might run into errors, and it's good to run into errors and then learn from them. So when we graph this, we're going to find the time right here, and it's going to be like 15 seconds. So we need our window. I'm going to go zoom 6, and then we're not going to see it, so I'm going to go Y, I'm going to go up to 15, and then the X, I'm going to go to 20. And then so there you go. So there's the graph, and it's going to cross at 15 seconds. So we get a value. But this is why this is a pain in the butt, because we have an x squared and we have to use the quadratic formula. And we're going to do it. We love that quadratic formula. Absolutely hate it. Okay, so we get a time frame, TU, of 15 seconds. So booyah. And that's solved. Like right here, this is the solution to the problem. And as long as you throw in any value of acceleration and any total time total, then you can find the uniform speed. So that's kind of cool. So if your time total is in a whole hour, t is equal to 3,600 seconds, and your velocity average is still 20 meters per second, or about 45 miles per hour, and you have an acceleration of 5 meters per second, well, I mean, at the end of the day, that's really easy. You're basically going to accelerate very quickly, go the entire trip a certain speed, and then decelerate. But you're going to go for a hell of a long time. We've just said that. You're going to be slightly more than 20 meters per second. You know what I mean? So do you want to do that one? I mean, yeah, let's, everywhere where we see 25, we're going to do 3,600. You know what I mean? And this is good too, just to have skills to be like, hey, I could do that. I could change up my variables without, needing a nap or something. Cool. So now our velocity, I think we can just graph it, and we'll have no. This is going to be the time. Obviously, the time for this is going to be like basically we're going to spend almost 3,600 seconds. So we have to go our window. This is also a good skill. We graph something and it's not showing up on our graph. Well, what's the time uniform that we're solving for? Well, about 3,600. If I have to guess, it would be 3,580. I don't know, seconds. So we're going to go all the way for our x to be 3,600. Going to graph that, and hopefully our graph's going to come right down. Yeah, it comes down so sharply. So now we can really increase this y to 3,600 and see if we can actually get a curve. So there's the curve coming down, and we're going to go a value of 3,500. We're going to get a 0 left bound. We can't even get a right bound, so we're going to increase this to 5,000, and we're going to do negative 3,600. You know what I mean? Oh, no, I didn't do it right. What didn't I do? Oh, yeah. Negative 5,000. No, what the hell? Holy Toledo. Yeah, we want x to be 0 to, oh yeah, there we go. No way. Bummer. Sometimes I just go zoom, sometimes it wigs out. So zoom 6, and then go back to your window, and then start changing. We're going to go negative, there we go, and we're going to go 5,000, and we're going to go negative 4,000 to 4,000. All right, heck yeah. So now we have that curve coming down. It is pretty easy. And then we trace it out, 3,500, 0 value, left bound, right bound, and then centered. Cool. So our guess was pretty close. We're going to be spending 3,592 seconds moving linear. So only 8 seconds, only 4 seconds to accelerate, and then 4 seconds to decelerate. Well, heck yeah, that's exactly what we found. If it's going to take 4 seconds to get up to 45 miles an hour. Remember that from the initial problem? So, I don't know. This problem is super satisfying to me, spending hours and hours on one problem, because you're really understanding, I mean, you're taking something basic, but you're having a thorough understanding. Because my goal is to actually, you know what I mean, start tackling quantum physics stuff. You know, not that I'm going to be leading the way in any regard, but being able to actually teach it so other people can have that nice step to be like, oh, hell yeah, I get this. You know what I mean? I'm understanding, because there's 100 ways to understand a simple problem, instead of just finding the magic trick to get there. Okay, so we are almost... so that all we did, so we found the equation, but now we're going to have to... we started we want to get the quadratic formula for this. So we need to get this in form of a quadratic formula. So right here we have an x, our variable right there is an x, and our variable right there is an x. So it looks like we have x squareds. And so we already got this in the form of, and now the other thing that I'm going to do to simplify this, because it gets a little confusing, is I'm going to say tu is equal to x. You know what I mean? So let's take this velocity average, and we're going to say that's omega divided by t. And t is just a value we know. You know what I mean? That's the total time. And then we're going to have t minus x divided by 2 squared plus omega divided by t minus x divided by 2. See, this is just a lot easier, times x. And now we can almost, we already did this one, we're pretty confident. So this value is going to, and I can just write it in. So we have omega t, and now we're going to say, hey, that's 1/4, like this squared, we already did it, is 1/4 t squared plus 1/4 x squared minus 1/2 tx. Cool, we did that. And now this part, heck yeah, we're just going to FOIL through the x. So this is just going to be tx and then minus, yes, there you go. And then we're going to divide by 2. So we're going to do this omega t, and then we're going to say this is 1/2 tx minus 1/2 x squared. So sorry I already put those in, but yeah, that goes to here. And now we can FOIL through the t. We should have done that a long time ago, maybe, because okay, so we still have average velocity is equal to, so now we have 1/4 omega t, so that's there, and then we have plus 1/4 omega, I'm just going to go t to the -1 to keep everything up top. That's also a good strategy once you get better, is like not having to throw things downstairs just to make sure everything's in a nice line. But right here we have x squared. So see what we did? We have 1/4 omega t to the -1 x squared. Cool. And then right here we have minus, so the half's going to stay, the t's are going to cancel, and we're going to have 1/2 omega, and we just have that x. Heck yeah. Now the t is a constant, you know what I mean? So don't think that's a variable. The omega is a constant. Those are things. Alright, my camera is definitely going to overheat another time, but we're going to push through. So what I was just saying was that, hey, in this equation, t is a constant, omega is a constant, because those are parameters that we choose. And it comes down to any equation. It doesn't have to be a constant. You could say that x is that time uniform, and I'm going to say, hey, I want that x time uniform to be 10 seconds. Well, it's kind of like squeezing the little things where the eyes pop out. If you do that, then your time acceleration, this t is going to change. You know what I mean? And then if you say, well, I don't want that to change. I want my time to accelerate. I want this to be 10 seconds and my time to accelerate to be 5 seconds. And I want the total time to be 20 seconds. You know what I mean? Well, then if you want that to happen and you still want that average velocity of 45 miles per hour with that original problem, or 20 meters per second, then you're going to have to, your acceleration is going to change. And then you could solve for acceleration. So with those. Okay, so we're just kind of picking that one parameter, and that's what the problem said, that time uniform. That's what we're interested in, and we want an equation for time, time uniform. Okay, and then once we FOIL these through, yeah, we'll be able to combine terms, and so we're gonna have plus 1/2. The t's are gonna cancel, omega x. And now we're going to have minus 1/2 omega. We still have that t, so we're going to go t to the -1 x squared. Well, look at this. We have 1/4. These two terms are the same. This is 1/4, and then we're going to minus 1/2. So we're going to get -1/4 omega t1 x squared. I'm just going to write that to the side because I definitely see that. Anything else that I see? This is just an omega t, but it doesn't have an x in it. This has an x. So we have 1/2 omega x plus 1. Oh, that just cancels out. So usually something like that happens and it's nice. And now you're just going to have this term. So we're going to have average velocity is 1/4 omega t. This is your constant part. And now you're going to have it minus 1/4 omega t to the -1 times x squared. And actually we don't need to use the quadratic formula because here we had another term of just x. We had x squared, we had an x, and then we had a constant. But this term cancels out. So now the easiest thing to do to get this into like a positive form is, hey, let's bring this over here. So we're going to go 1/4 omega t to the -1 x squared. Now, this is why you don't solve problems with letters, because at this point I have no check on reality except for, getting the answer and just making sure it has a check at the end. But like doing these steps, this is where math is cool, because if you use the axioms of math, like these relationships will always stay the same, even though you're moving things from one side of the equation to another, dividing things out. And that's a fascinating aspect of math. So now we're going to say this is 1/4 omega t, and then we're going to subtract that average velocity. Okay, so now here we can multiply by 4. So let's do that first. We get omega t to the -1 x squared, and now we're just going to have omega t and then minus 4 average velocity. Cool, we did that. And now we're going to divide by this omega. So we're going to have t to the -1 x squared, and now we're going to have t minus 4 velocity initial divided by omega. Cool. And now this t is downstairs. This is the same thing as x squared divided by t. And so now we can multiply by t. So now we're going to have x squared is equal to t squared minus 4t velocity average divided by omega. Cool. And now we have x. Now we just take the square root of all that. So we have our total time squared minus 4 times our total time squared. Just our total time times the average velocity divided by omega. And we're going to take the square root of that. And this is our time uniform. We've already identified, we already made that switch on variables. So now what we can do, we can say time uniform is the square root. And are we using all the variables that they're using? I just have to make sure that this average velocity, is this, because that's what they use. And so we have, and they use this funky tau for time. So time uniform is time squared minus 4 times the average velocity divided by the acceleration. And there's our equation, you know what I mean? And I'm sure there's hella easier ways to get there. But that was my way. And we just need we need to check on reality. So we're going to go 25 squared minus 4 times 25 times 20 average velocity divided by 5. And then we're going to square root that, and we get TU at 15 seconds. Holy hell. So I don't know if I'm actually going to, solve the problem from the beginning, because this one stands alone, you know what I mean? It's just like, hey, you learn a ton to get to here, you know what I mean? The understanding is not to just use letters on this problem, but just having a thorough understanding of, and I'm excited to do problems like this, throw some numbers at it because it's easy. That's the easy, juggling part. And then see what the relationships were, get some equations going, and then see finally why those equations are coming together the way they are, and so then you can get relationships. And it's just fascinating to me that yes, we do have an equation here, this is an equation for the t uniform as a function of that total time, as a function of that average velocity, and as the function of acceleration. So it's exactly what we set out to do. And heck yeah, let's write it one more time. T squared minus 4t, average velocity divided by omega. But yeah, I don't know. I'm just considering that these are first chapter problems, that these are easy, and I'm just making them extraordinarily hard. But I just don't think so. I think just the way they're worded and they go about them, I don't know. It'd be fascinating to be like, just watch somebody else do these, and it's just like, oh, no duh, no duh. But I mean that equation is still pretty complex with a square root and your time squared and another time value over there. Average velocity divided by acceleration, times 4. I don't know, but there it is. And again, this equation only applies for the time where your acceleration is going to be the same accelerating as decelerating. All right, so hell yeah. So thanks for joining me, and guess what? That's a video.